everything else versus Bitcoin essentially gets spent and dies.
I want to be able to have reactive security, and I think Opvault is today the most straightforward, easiest to use way to do that.
I will not be insulted by a clockmaker.
Overall, these kind of ways to make the network easier to both build on and interact with, I think is a really big deal.
If Bitcoin existed when we started Twitter, we would not have to go down the ad model path. I mean, it's simple as that.
Integrating Lightning into a social network is the killer app.
Hello, and welcome to the Bitcoin.Review podcast, where we explore developments and projects with the people who actually make them happen. The show is supported by Pod 2.0, Sat Streaming, and CoinKite. If you're a new listener, I'm NVK. I run CoinKite, where we've been helping people secure their Bitcoins for over a decade. We make the cold card and fun products like the block clock. You can find more information about it on coinkite.com. So guys, we just finished the episode, but I decided to record a little preamble for this one, which we don't normally do. And it did get a little dense in terms of like complexity of things, but I really think this is one of those episodes that you should like stick it out all the way to the end, because there is this really nice arch that builds and it sort of like gives you a round understanding of like how each of these complexities that we talk about leads to the next and why and how we got there. We essentially address the inscriptions, I think, in the last 10 minutes of 2 hours and 10 minutes. So stick in there if you can. I think it's worth it. And I think you're going to come out like understanding Bitcoin a lot more than you did before, even if it's through osmosis. Hello, and welcome back to the Bitcoin.Review. It's been probably a week or two of hiatus. I was in the sun breaking coconuts in Costa Rica for Nostrica 2023, which was fantastic. And what a way of coming back. I mean, like I have like two rock stars here. You know, this is the perfect show to say I am not a cryptographer, but these guys are. So welcome, Andrew Poelstra.
Hey.
So do you want to just tell us, I mean, people kind of know you, but like just sort of like what's your the things that keep you busy right now?
Yeah, for sure. So I'm Andrew Poelstra. I am the Director of Research at Blockstream. I've been involved in a number of privacy and scalability things over the last several years with confidential transactions and scriptless scripts. Some people think I'm the Mimblewimble guy, stuff like that. Lately, I've been focusing actually less on privacy tech and mostly on two things, really. So one is simplicity, like scripting, trying to think how can we make Bitcoin script be more expressive and stuff. And the other is a kind of a passion project for custody, where I'm trying to figure out how to store secret seeds, like BIP32 seeds that define all your keys. I have a way of checksumming these and splitting them up entirely by hand using kind of these worksheets and these paper computers called Volvels. I've got one on my desk here with this beautiful artwork.
Oh, I have one of those. You gave me one of those at Miami last year.
Yep, I did. So we're hoping, we're working on getting a print shop, like a real professional one. Here's one of, this maybe is one of the booklets that I showed you or gave you. This is an early print that were like hand bound and stuff. So hopefully we'll be able to see that on the Blockstream store in the coming month or two.
Very cool.
It's been a job of printers. So.
Adam Waxwing.
Hey.
Or Adam Gibson. How do you want to be called, sir?
Waxwing's fine.
Okay. So Adam, you do a lot of different things right now. What are you busy right now with?
I'm busy sort of with non-Bitcoin things, to be honest, to be perfectly honest. Not doing that much at the moment, but I am still doing bits and pieces. I'm still doing join market stuff, maintenance, and just sort of improving little edge cases there. I recently spent a lot of time getting very enthusiastic about like ring signatures, linkable ring signatures, and other like related things that I'd love to talk to Andrew about for the next 2 hours, but it might be slightly off topic.
Yeah, totally out of scope.
Because me and Andrew, we meet on podcasts about once every 3 or 4 years, and I send him a message on IRC about once every 3 years as well, and that's about it. Which is a shame because I'd much rather spend lots of time talking to Andrew.
You know what we can do, right? We can after we're done with the topic of hand, we can just let you guys just talk and keep on recording, and then play that as a second episode.
Yeah, I'm not sure if people would enjoy it, but who knows? Who knows? I mean.
So I think, as usual, I forgot to introduce the actual show itself, what we hope to do today, which is we want to explain segregated witness, like reasons why, how, what, talk about a bit of Taproot witness, sort of like get in there and get people to kind of understand like what the stuff is, what it's for, and the reasons why we have it. It was a fundamental change to Bitcoin, right? I mean, Bitcoin had your standard transactions back in the day. And then we had the massive uproar when we got P2SH, right? And then like we still had the issues with malleability, and that became very clear because an actor was sort of deliberately just swapping them. And that caused the people who wanted, zero confirmation transactions, which doesn't exist, for payments, and caused a lot of grief. And the story is long. I'm not sure if it's worth sort of like getting really like back into the history here. So who wants to volunteer to explain, I think, the first part of this, which is why BEC32? Like, why did we change the address type? Why did we need that?
Sure. Well, I can take that since I'm thinking a lot about BEC32, since we use a very related checksum for my Volvo booklet. I should stop stealing it. You can't actually buy it yet. Like we're still trying to get the printer to put stuff on the right side of the page.
I'm still waiting for the print edition of your table of discrete logarithms, Andrew. I want a copy for my bookshelf.
I might have a use for it, so we might do it. We'll circle back. So BEC32. Yeah. So let me talk a little bit first about Bitcoin's existing, or the legacy address scheme. Well, first off, let me say what a checksum is, what the purpose of this is, right? So when you have a Bitcoin address, typically you'd get this address from somewhere, you would copy and paste it, right? You want to put it into your wallet. And you want to avoid typos, right? So there's a risk that like maybe a bit gets flipped, actually. I've seen this happen where you're sending stuff over a crappy communication line, or there's a cosmic ray happens, or, even if you're copying and pasting something, there can be risk of a bit flip. So we have what's called a checksum on this, where basically if you change an address in kind of random ways, then the resulting address will be invalid. So your software will immediately recognize, hey, something went wrong, probably you only made one or two mistakes or whatever, and then the software can definitely detect that. And so the way that the old address scheme worked is that it would take the kind of raw data of the address and do a hash of this. It would take a SHA-2 hash of this, and then just take the first 4 bytes of that SHA-2 hash and tack it onto the end. So the idea is if your address changes at all, then with very high probability that hash will change, right? So if you flip like 1 byte but don't change the last 4 bytes to be exactly what it now needs to be, then it'll be invalid. So you can, with very high probability, you're going to detect any mistakes, and we can make that concrete, right? You can say 4 bytes. There's 2 to the 32 possibility. This is about 4 billion. So there's a 1 in 4 billion chance that a legacy address, if you tweak it in some random way, there's a 1 in 4 billion chance that your software is still going to accept that. So that's really good, but there are a couple problems with this mode of checksum. So one is that the 1 in 4 billion is not 0, okay? And you may be surprised that we can actually get it to 0, and I'll talk about that in a sec. The other is that it's kind of slow and complicated, right? So it's frustrating if you're writing software, if you're writing block explorers, if you're writing like high volume wallets and stuff. It can be very annoying to have to do all these SHA-2s, right? It's a fairly expensive hash function, and you have to truncate it, so you're not even using most of the bytes and so on. You have to do it twice, because Bitcoin loves to do SHA-2 twice. So that's Satoshi. Just to make sure the first one took, right? You gotta just hash it again. And then I guess another issue is that because in principle, 1 in 4 billion times you flip a bit and the address is still valid, you can't correct errors. There's no like mathematical way that you can really correct. You sort of have to grind through. If you had an address that was corrupted, you would have to kind of grind through all the nearby possibilities. And if one of them turned out to be right, probably you're okay. So BEC32 brings in a checksum scheme, what's called a linear code. And This is a scheme where it's actually guaranteed that any two addresses have at least 4 differences between each other. And what that means is that if you have 3 or fewer mistakes in your address, then the chances of that being accepted are 0. Not 1 in 4 billion, but actually 0. And there's even a cooler fact about this, which is that because you know that there's no 2 valid addresses that are within 4 things of each other, that means if you make 1 or 2 mistakes, there's a guaranteed unique address that is within 1 or 2 mistakes of your result. And what that means, and you can efficiently find it. So what that means is you could actually correct errors in principle. Now, you shouldn't, in a lot of contexts, you really shouldn't, like, if your thing is corrupted, you should go back and, like, ask whoever gave it to you to resend it, right? Like, better to be safe than sorry. But in principle, if you've got an address that, you stored somewhere and you, like, left it under the ocean for too many decades, and then here, like, 1 or 2 things are broken and the original people were in the shipwreck, I guess, in this story I'm telling, then, you just got to correct it. And Best 32 lets you do that. So we have a much stronger checksum that has guarantees, at least if you only make 4 or fewer errors, it's guaranteed to correct stuff. It's way, way faster to compute. It's incredible. You just take the data, you kind of multiply it in some abstract sense, and you just add them all up. So you just add through, you've got, a 40, 50 digit address. And you just add them all up. You can do it in, tens of nanoseconds kind of thing. So that's the motivation for switching to a new checksum, right? So that's one thing that came with this. Then the other thing that came with Best 32 is that we had an opportunity to change the character set. So the encoding of the legacy addresses, and this is actually probably for most users the more important thing, the encoding was in something called base 58, which is just a crazy, I think Satoshi invented this. It's kind of a crazy scheme, where you take all the letters of the alphabet in lowercase and uppercase of the Latin alphabet, and all the numerals, except we drop 1 because it looks too much like capital I, and I think we dropped capital I for the same reason, and capital O, and I think there's a couple of characters that we dropped because they look too much like each other. Okay, so the result of this is that you have a case-sensitive address scheme, which really is just like the worst. So the benefit of base 58, the benefit of having all these extra characters is your addresses are a bit shorter, but as a result, if you're trying to tell someone an address over the phone, you can't do it. That's like a fun experiment. Try it. Call your friends and try to communicate to them.
The idea of somebody giving a Bitcoin of any kind, even a Back32 over the phone, it would be it's torture. For sure. You just can't.
But
you know what's funny though? If you are using a case-sensitive piece of software that, say, for example, only does uppercase, right? So it's a very, very small subset. You cannot send a Bitcoin address. Yeah. Like on ham radio, when you're doing Morse or you're doing something else, it's uppercase only. You literally could not send a legacy address.
Cool. I didn't know that. So there's a similar issue.
You could send uppercase A, like UPPERCASE A, lowercase.
Oh no.
Q.
Yeah. The QR codes are similar, right? So you can't send mixed case and QR codes, but it's much less efficient, right? They prefer if you just stick to one case and it be uppercase. So Best 32, we got rid of that, right? We said there's no more, it's just one case, right? And kind of by default it's lowercase when you're writing it on your computer, and it's uppercase when you are sending it in a QR code and stuff. But there's only one case, so it doesn't matter. And Peter Willa, who cannot do anything halfway, he found some sort of way of measuring the visual distance between characters, and using that he chose which characters to throw away, because we have 32 characters, right? We have the 26 letters of the alphabet, we have 10 digits. Okay, that's 36. We get to throw away 4, so we threw away the letter B because it looks too much like 8, and we threw away the capital 1 because it looks like just absolutely everything. We threw away I for the same reason. And we threw away O, right? Because O also, circles and lines are no good. And so we wound up, and I don't know how good, I can see the lights kind of washing it out, because I've got this booklet with me that has the binary to Best 32. So we got to choose a new alphabet. So we got rid of the mixed case thing, and we probably improved the legibility, because legacy addresses did have things like 1s in them that were kind of ambiguous, and you could confuse with other characters and stuff. So we got just a better checksum. We got rid of the mixed case. We improved the legibility, I guess, right? The set of characters that we threw away. Yeah, so we would just say, and these were all problems that...
Yeah, so the most important part is we got checksum, right?
Yeah.
And we solved like a few of Satoshi's quirks, right? So,
well, we had, to be clear, we had checksum, right? You're saying
Yeah.
it's just a much, much better, as Andrew has explained in great detail, it's a much better version of it.
yes. And I don't think most clients were actually doing the checksum on legacy address.
Really?
I think,
Which
I
one?
think there used to be some issue.
Surely all wallets were actually calculating the checksum on address.
No,
You have to
there were
validate
a
it.
bunch of them
One of the
that
most
weren't.
important things you have to do when you write a wallet is verify the address is valid.
No.
Otherwise, you're sending money into the void.
In the early days, there were plenty of wallets that were not checking checksum.
Oh, the early days,
early days, like not even that early. But anyways, okay, so we got a better address, right?
Yeah.
Now we had to address the malleability issue.
Right. Yeah.
Go ahead.
I can keep babbling, but maybe we should let Waxwing take this one. You want to talk about malleability and the history there?
The malleability, yeah. I'm a little bit unclear on the history. I know you said you didn't necessarily want to delve into the history too much, but it is kind of interesting.
Yeah, no, we don't have to talk. Like we had to address it, right?
Yeah,
so,
but for example, like my exposure to that, I mean, I was still pretty new into Bitcoin in early 2014, right? But in that time, the whole Mt. Gox story was so massive and everyone was talking about it. And then, Carl Pellis came out with a statement at some point during that whole period where he was saying, look, this is the actual reason all the money, I can't find it. It's because of the malleability. And there was so much controversy around it. And there was huge confusion because like 80 to 90+% of people had no idea what the concept of malleability applied or meant here. But I have a feeling that I'm misremembering the history. And there were actual incidents of, was it exchanges or something that were not dealing with malleability properly?
Most clients, let's put it this way. Most clients were not dealing with malleability because we never really had the issue. There were a couple accidental flips, right?
Yeah.
But like, I don't think he even registered to most that this was a concern. It's just that like we had an actor that came into play that was flipping every single transaction in the network on purpose. So essentially like DDoSing the network with inverse S, right?
Right. So if I could, I went about this the wrong way. I started talking about history. We should start talking about what the hell we're talking about, or what is malleability? What is
explain that?
Okay, so the concept here, I think, it's really kind of a profound concept, and I think you can, putting my teacher hat on, you can explain this in kind of a nice way. That what you've got with the transaction is you've got like a statement, just like if you're signing a statement, you're saying this thing is true. When I want to spend money in a Bitcoin transaction, I'm signing the statement that this transaction is something that I authorize. It's fundamentally an authorization process, isn't it? Saying this action can go ahead because I say so, and I'm proving I'm the person who has the authority to make the authorization, right? So the simplest way to explain the issue of malleability, I think, is that when you're signing a statement, you don't want... what you're authorizing is the transaction. The money goes from A to B. I'm not authorizing a signature. I'm not authorizing anybody else's signature or any other signature. A signature is not the action. A signature is itself an authorization. And in Bitcoin, we're dealing with multiple different signatures at the same time, right? We might have many inputs being signed. So we don't want to sign data which proves that the transaction is valid or that authorizes the transaction. We want to sign the actual decision itself to move the money from A to B. And it turns out that because it just a sort of quirk of history, I guess, that ECDSA, the signature algorithm that we use in Bitcoin, which is a sort of very much or at least was an industry standard at that point, is very easy to like take a signature and change it. So at some point we're going to have to get into like third party and first party malleability and all this, right?
No, but see, we don't have to go that deep.
Yeah, we don't go that deep. But just to illustrate the point of like the point of where we're going to get this history point you're making is it's a real problem because signatures can be changed not only by the person who makes the signature, they can make a new signature, it's not difficult, but somebody else could change your signature, and that's the worst kind of malleability because ECDSA doesn't have what's technically called strong unforgeability. So, in other words, somebody can look at your signature, which authorizes this transaction, and say to themselves, "Oh, I'm going to be evil. I'm going to take your signature and just flip it in this weird mathematical way." The signature is going to change, but it's still going to be your signature.
They're just turning it upside down. It's still the same signature.
It's the same signature.
One way I like to describe it is imagine I sign a document by saying I agree in lower caps. And then somebody takes that and makes it uppercase.
Yeah.
It's still my sort of agreement,
Your authorization,
right?
yeah.
But it just looks different, so the software gets very confused.
Yeah.
And then it doesn't know what to do with it, right? Because it's like, hey, the result matches, but the signature looks weird now. So like it gets very tricky, because if your software is not prepared to receive that, now you don't know what to do. And when people are depending on signatures instead of confirmations for a transaction, now they're depending on something that could be changed, right?
Yeah. So overall, we get this situation where, okay, we just discussed how signatures could be changed. And the problem here is that when we sort of define what a transaction is, we kind of watermark it or mark it with this thing called a TXID. In Bitcoin, we tend to use this abbreviation TXID for transaction identifier or transaction ID. And what that thing is it's supposed to be like encapsulating the whole transaction, right? It's supposed to be defining what the transaction is and give you a simple 32-byte, just very short string, which everyone who's ever used the Block Explorer has seen this. This is like, oh yeah, that's the transaction ID. That's the identifier for that transaction. That thing, pre-SegWit, included all of those signatures, all of those things that authorize the transaction, but were themselves not part of the transaction. And so that's why we had this crap show of, I've made a transaction, its transaction ID is ABCD, blah, blah, blah. And then an hour later, somebody else out in the world, we don't even know who they are, has decided to somehow rebroadcast it in a way where it's got a different identifier. And you can imagine for a wallet developer, it's a nightmare.
And it would get confirmed. Yeah, and it would get confirmed, right?
Yeah.
I mean, you'd have...
It depends, right? It depends which one gets confirmed. I mean,
right, sure. But you could have it so that the different transaction ID would get in a block.
Yeah. Yeah, and as a wallet developer, that's a nightmare. I mean, it's not impossible to deal with it, and of course, you should deal with it in a pre-SegWit world. But of course,
we all end up having to do it.
It was a new technology that was moving fast, and people were really struggling just to make sure people didn't lose their coins, like you say, like not verifying address checksums. So you can easily imagine that plenty of people didn't actually get on top of this in the early days.
It was very painful. Okay, so we have this problem.
Yeah.
Okay, somebody's flipping the signature here.
But I prefer that if you go to that deeper level, it's really important, I think, because all this stuff about witness, and then we'll end up talking about block sizes and weight and all that comes from that core, like, you have to have that mental model in your head that there's two separate things going on. There's the actual...
Okay, but how can we explain this in farm terms?
But that's in farm terms, right? Farm. I've never been on a farm in my life. I don't know how to explain it in farm terms. I'm a city boy.
I'm okay if we get in there, but like I think that if we
I don't want to get I don't want to get like technical. I want to get the right mental model, right? If you have the mental model, there's this thing which is a transaction. Alice pays Bob. And there's this other thing which authorizes that transaction. You can clearly see, if you have that right mental model, that you shouldn't mix the two up. And lots of things go wrong if you mix the two.
Well, you can use the envelope.
Oh, yeah,
You can kind of use the envelope model, right?
What's the envelope model?
So, the envelope is like the transaction, right? You have all the parts of the transaction inside the envelope, and the signature goes outside of the envelope. And then we can have it so that what we decided to do is not even put the signature on top of the envelope. The signature just refers to the envelope, and they're not even together anymore.
Actually, yeah, I did a whole talk about SegWit in London about a year ago, and it was all like that. It was because actually the model you're talking about is more like the whole Xiaomi and blind signature thing. That is a really cool way to explain that. But here, this is just signatures, not blind signatures. So the envelope element is.
But the idea kind of works.
What I did was I used like
it's a clear envelope.
No, but what I did was I used Post-it notes. You have a poster. No, but you have a poster, and the poster has all the transaction, and then the signatures, all the witnesses are these things that you're attaching with little Post-it notes on the side, and you just kind of move them around. It's just that fundamentally all it comes down to is you have to have the correct mental model. There are two separate things, and this witness attests.
Okay, let's pick one. Okay, how about this? So that we don't get too much into the weeds versus like blinded versus non-blinded. Let's say it's a postcard. Okay, all the information is in the clear here, right? One side of the postcard is going to have like all the details about the transaction, every little bit of it. Okay. And then on the other side of the postcard, you have your signature. And that's how it was. It's a single piece thing. You cannot separate the two. That's how the transactions were, right? Everything bundled together in the clear as a package. Mm-hmm. How does that feel?
Sorry, I was just thinking, can I upload a picture? Sorry, I wanted to show you a picture, but never mind. Yeah, that postcard thing works.
So what if we said the signature was a stamp? And on a postcard, I guess
sure.
it's pre-printed as a stamp.
No, it could be. No, you could put a stamp on a postcard. Mini are not prepaid.
Okay.
There you go. Perfect.
Yeah.
Let's use that.
The problem with the stamp is it's like you're fixing it in there and you can't separate them. It feels like the thing that you're trying to do is separate two things here.
I know, but that's true for pre-SegWit, right? So pre-SegWit, we have an inseparable part, right?
Oh, you want to look at that?
There you go. And there was somebody on the network that had a little special machine that they can just like lick the stick, the stamp,
Right.
and turn it upside down,
Yeah.
and your reader can't read it anymore.
Yeah, good.
Okay. Yep.
Okay, like none of these things will ever be as like perfect explanations, but like we need something that people can relate to. So we have our postcards. Somebody can flip the stamps, but the stamps are still related to the post to the postcard. And say like you had an extra like a ink stamp on top of the stamp, so you can still like revert it around, but they're kind of related. Anyways, so that's how it was, right? And because all these things were all as a package together, you could do this attack or accident where you could invert the stamp and then it confuses everybody.
It's quite cool, that, yeah.
So now comes segregated witness, right? Where we're essentially trying to separate the signature, right, from all the other stuff because they don't have to be together. So who wants to give like a very short sort of like a primer on segregated witness?
Sure, I will. While Waxing's trying to upload pictures here. So
and failing, by the way.
So let me flesh out the stamp analogy just a little bit more.
Sure.
I put a stamp on the postcard and I send it to you, and then I text you, right? I say, hey, did you get my postcard? Like here's a picture of it. Right? In the picture here is the TXID. I say, did you get it? And you say, oh, I don't know. Like I got this other postcard, but the stamp's upside down. So no, like. I don't know anything. Like, I guess yours got lost, because it's just this upside down stamp one that nobody knows where it came from. And so you can see how, like, if you were a wallet software, you can get confused and think that there's multiple, or think that something got lost, or think that something came from nowhere. And then it's a problem. And ideally, you could get somehow I could send you a picture or like a TXID that didn't have a stamp in it. And you can imagine, and it gets worse, right? Because you can imagine, now certainly I can replace a stamp. What if we're doing a multi-signature? So I got to put a stamp on it. And then Adam's got to put a stamp on it. Well, now I don't even know what Adam's stamp looks like. So how can I send you a picture kind of thing? So in SegWit, what we did was we said, well, the TXID is going to cover all of the normative transaction data, all the data that actually shows where did the coins come from, where did they go, what's the fee, that kind of stuff. And we're going to add a new field to the transaction called the witness field. And that witness field is not going to be covered by the TXID. And there's actually like some very clever things going into this design, because initially like we kind of had this whole transaction, it was all stuck together, we needed to break it apart, and we were pretty sure we would need to do some sort of hard fork to like completely change the transaction structure. And hard forks are scary. Like even like all maybe we'll get into it, but the politics of hard forks versus soft forks effect, just as a technical thing, right? Hard forks are very difficult to engineer because you got to have a flag day. Everybody's got to update at exactly the same time. You got to coordinate it, much more than you do with a soft fork. And already coordinating a soft fork is kind of a nightmare. So you're kind of this is kind of a difficult thing. And it was actually Luke Jr., I believe, who found like this clever thing where he's like, oh, what if we just added a field and the TXID didn't cover it? And then there's a few subtleties in the encoding there but basically we were able to do this in a way where we were just adding something and then like forgetting to stick it into the TXID with everything else. So, okay, so now you've got these transactions where you've got a transaction, you've got the authorization, and the transaction can be identified just by what it does. But now, well, you got to keep track of the authorization, right? Like the network needs to know the transaction with all the rest. The network needs to notice if there is malleability. The network should still notice that, believe it or not, because something has to wind up in the blocks, right? And ideally, if you want the network to kind of agree on the entirety of the transaction data. So the things that get into blocks are, even if they have different signatures, they're clearly the same thing. But you still notice and you still know you have to refetch and have to re-verify a signature because it's not the one you saw last and blah, 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 blah. So we introduce a new thing, the WTXID, the witness TXID. And this actually covers the entire transaction. So now we've got two objects here. We've got the TXID and we've got the WTXID. And both of those go into blocks. I really want to emphasize that, because a lot of the confusion around SegWit was the idea that by not covering stuff with the TXID, it somehow wasn't in the chain, or it wasn't part of the transaction, or like it was kind of floating out there in a way where you had to just hope that somebody had this data, and there was all of a sudden a potential.
It's not Bitcoin. Yeah. It's not Bitcoin because it's not a chain of signatures. Remember that one. That was the big
exactly.
slogan.
But
that's right.
The truth is we have this WTXID. We have a WTXID which covers the signatures, cover the witnesses, and that is committed in the block. But where the WTXID is not used, and here's kind of the magic of SegWit, right, is when you create a transaction, every input refers to an old transaction, because every transaction input is an old transaction's output, right?
That's the whole point of Bitcoin.
Yeah, exactly, right? It's a chain thing.
This is it. This is literally Bitcoin.
Yeah. So when you refer to old transactions, in that specific instance, you use a TXID and not the WTXID. And that means that when you're chaining transactions off of each other, that it doesn't matter if the witnesses get replaced or changed, you don't know them ahead of time and stuff. And so now you can do things where you have chains of transactions that might be re-signed, or might be incompletely signed, or whatever you want.
Before they're broadcast or confirmed is the crucial point. You can chain things together without,
So we actually get two benefits here. So your wallets are now saved, because they can just say, here's a TXID, and the TXID won't change unless the transaction actually is a different transaction. So now your wallet accounting is way better. But also on the network level, right, we can say our transactions refer to each other in a more robust way. And this solved like 1,000,001 technical issues with multi-signature transactions where you didn't know the TXID, whereas with Lightning, where you have unconfirmed transactions, where you have two parties that are constantly re-signing kind of the same thing, slightly tweaked, like just any hope of chaining unconfirmed transactions. Faraway lock time transactions are another one. You create a transaction, it's lock timed a year in the future. Well, you can't broadcast it. It's not a legit transaction until the lock time's up. But you don't know it's TXID, right? 'Cause you've got a year in which the signatures could be replaced or, malleated, or, who knows, right? So how do you keep track of the transaction without an ID for a year? And the blockchain won't help you, because the blockchain won't accept it.
And a third beautiful thing too is that because of those essentially double verification feature, in a way, you don't have to store that witness data in your computer, right, forever or for everyone, because that is not required after a certain amount of blocks anymore for you to have those older transactions to be known valid.
Yeah, that's right. That's right. So in a lot of context, when you're running a node, you're willing to accept transactions that don't have the witness data associated with them. And this is another point where people got really kind of confused and scared, because there's fear that like everybody will suddenly be just like running these nodes that don't just throw the witnesses away kind of thing. Well, you can't really run a full node that way, and you can't really run an archival node. But what you can do is when you are running a wallet, for example, you can receive entire blocks and entire transactions, and maybe you're willing to just accept, because you're like a retail wallet kind of thing. You're not trying to be a Bitcoin full validating node here. You can accept transactions that aren't relevant to you, and you don't check the witnesses. You say, you know what, it's in a block, it's buried a whole bunch. Or maybe it's not in a block, but like, okay, if it has no witness, it won't get in a block, so eventually it will kind of disappear. I just don't download the witnesses. And prior to SegWit, if you tried to do something like that, if you tried to say, I don't care about the witness data of transactions that are relevant to me, you're kind of in trouble, because now you can't vet the TXID. Like, you need all the data, you got to feed it into a hash function to get the TXID. So you don't know the entire transaction, you can't really recognize it in a block. Anything that spends from that transaction, all the things that are chained after, you can't recognize those either, and so on. And eventually, it's probably going to become relevant to your wallet, but you're kind of stuck, right? Like you can't figure out the state of the chain. So now you can. So now in these contexts where you're willing to drop witnesses or not receive them or not store them or whatever, you can do this. You can do it selectively just for transactions that are deeply buried or that you're sure you don't care about, or blah, 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 blah.
Say, for example, JPEGs. You can just drop them. You don't have to hold them in your node.
Exactly, right? So yeah, we can get further into that. But yeah, absolutely.
No, wait in a bit.
if you're going to throw crap into the blockchain and it's in the witness field, if there's an efficient way for you to recognize it as crap, you could actually just refuse to take it.
I mean, we did get a lot better pruning and a lot better assume valid heuristics, right? Because of all this.
Yeah, that's an interesting, like, to try to draw the causation there. But yeah, absolutely. Trying to do any of the stuff that we've done. So SegWit's been active now for
Yeah, it's been a while. I know it doesn't feel like it because we're all scarred, but it's been a while.
the BIP has dated 2015, and I remember it activating in the summer of 2016, I think, right? So we're
No, SegWit was activated in late 2017.
Really?
2017. You're a year off.
Oh,
It
okay,
was
so the BIP
September.
date, okay, fine. There was a whole year.
2017.
There was a year of drama. That's in my head.
That's right.
How can you forget that year, man? That year was insane.
How can you not want to forget that
I
year?
wasn't thinking so much, but all right, thank you. Thanks, Fox. But okay, all right, 2017, right? So it's been 6 years. And yeah, a lot of this, like the assume valid stuff and the pruning and all this kind of stuff, right? We've done in a world where we had SegWit. And where we could assume even that the majority of transactions were SegWit. And we could say, well, the legacy ones, we're going to have to do something inefficient, but whatever, there's not too many. Yeah, doing it without SegWit. It would be harder.
It's been very hard.
It would be harder, right?
Very, very hard. It's one of those things that like we got so much benefit from, right? That it's almost like we forget what it was before. I mean, it's kind of funny because our store is still running legacy addresses for the shopping cart because the wallet that we built, it predates SegWit, and like it's just too much effort to change it until we actually have to, which we will in a year or two. Yeah. But it's kind of fascinating, right? Like, and to me, one of the most special things is how backwards compatible this whole thing is, right? I mean, we're literally running a shop with volume that is using legacy addresses alongside SegWit addresses. And like everything just works. It's quite beautiful. So, okay. So now we sort of explain some of the benefits of this. We explained that what we're trying to do here. So I guess like, why does the segregated witness has a discount, right? Why this witness has a discount, but the UTXOs don't have a discount? Well, because you can dump the witness. I mean, it's not as required to be stored in a drive and is not as important as the UTXO data. But like getting a little bit more technical, why can we have two pricing models for these two parts?
All right, so let me start by saying, so it is true that the witness data we can kind of throw out. So that does make it like kind of inherently less costly to the network. So we can give it a discount in that way. Another thing, so we had, for a long time before this, right, there was a lot of pressure and drama around increasing the Bitcoin block size. And this is something that we did, like I think everybody kind of wanted to do technology, allowing it kind of thing. But there's this one specific problem that I think was the biggest thing that was called quadratic hashing. And maybe you remember that phrase from the 2016 era, people throwing this around.
I was literally just reading about that for the last half hour before this interview because I really want to remind myself about that. It's kind of important,
Yeah. So the idea behind quadratic hashing is that if you structure your transaction in a certain way, you can basically make it so a validator needs to hash, n squared amount of data. And in principle, Bitcoin will let you have an entire 1 meg block that's all one transaction. So if somebody were to create such a block where it was all one transaction that was structured carefully, you have a mega block, you got to square that, right? So a meg times a meg is, well, if it was literally just squaring, that's a terabyte, I guess. So it wasn't quite that bad. It was, many gigabytes of data that you just had to feed into a hash string. And it was ridiculous. It was the same transaction data over and over. You just got to keep doing it in order to figure out what the whether or not the signatures are valid. And I believe somebody did actually produce a couple of blocks like this that took like 20 plus seconds, right?
That's right. Yeah, I was just looking up before the thing. It was about 25 seconds was what was being reported for this 1 megabyte block of like 5,500 inputs or something like that.
So, right, if it was taking this long to validate that, well, if you double the block size, it's quadratic, so you're quadrupling that. So already you have this is already a problematic thing. And then, right, you double the block size, which people generally felt that wasn't enough, right? I mean, we can debate about it, but you double it, maybe quadruple it, you try to multiply it by 4, which is what SegWit roughly did, what it did at maximum, right? And then you're 16xing this thing. So already you're taking, dozens of seconds of your CPU burning out just to verify one block. Well, you multiply that by 16, and now you're validating past when the next block comes in, and now your network doesn't work, right?
Could I just clarify that it's not just a problem that like individual node runners will have a lot of extra burden, but it really screws up the mining process, because the mining process is kind of critically dependent on the verification of blocks being very, very much smaller than interblocked arrival time, because if it takes a long time to verify blocks compared to how fast blocks come through, then you can as an adversarial miner basically sort of shut everyone out by just creating blocks that they're taking so long to verify, and you're so far ahead of them that you're just going to overtake the network. So it's absolutely like existential threat to Bitcoin to have a slow verification. It's an existential threat.
Essentially, a miner needs everything to happen on his work, right? Yeah. Before the next block. Otherwise, he loses every block. And that's true for network speed. That's true for his download of the block. Yeah. It's an integral part of Bitcoin's very basic speed issues, right? Or like that dynamic cannot change, right? We always have to keep the dynamic working that way. The miner needs to be ready to package a new block and broadcast a new block. And try to mine a new block, before the next block comes.
Yeah, absolutely. So with SegWit, so the reason that this quadratic hashing happened basically is for every input, for every signature, you would hash the entire transaction to validate the signature, but you tweak it slightly for every input. You hash the whole transaction, tweak it, hash the whole transaction, tweak it, right? You're just repeating. And that's where the quadraticity happens from you taking the whole transaction, that's n, and then you do it n times with n squared. With SegWit, we changed the signature hash algorithm because as soon as you're adding like a new place for signatures and a new encoding for all these things, you have freedom to change it. And so we changed it so basically just goes through the whole transaction once, and it just hashes the particular things that it needs, right? And then you have a single hash. So you have a single hash that covers all the outputs. You have a single hash that covers all of the input data, and a single hash that covers all the sequence numbers or something like that. And then for every input, you take those hashes. So now rather than being a 1 meg transaction, it's a 32-byte hash. And you take like all the pre-computed hashes and a bit of input-specific data. All the hashes and a bit of different data. All the hashes and a bit of different data. And now every time I move my hands there, rather than feeding, a megabyte, a million bytes of stuff into here, now I'm feeding like 96 bytes, right? It's just a few hashes. So that gave us the ability, this SegWit kind of, and just as an aside, another issue with increasing the block size. So like it seemed like it would have to be a hard fork, right? So SegWit magically comes in, it fixes a quadratic hash thing, and it gives us a way to soft fork in a block height, right? Or a block size increase, right? It was really just kind of this miracle bundle of technical improvements that weren't even the improvements that we want. Like the point was to segregate the witnesses, right? That's what it's named for. Yeah. And then just kind of as a bonus, we got this extra stuff that allowed us to increase the block size. Can
I just ask? Yeah. Sorry. Can I just ask or clarify the sig hashing, the correction of the quadratic sig hashing by having this pre-computed list of prev outs, a list of previous ins, and all that? Could we or could we not have done that without the SegWit part itself?
Yes. Yeah, we would have had to replace.
We could have, right?
This is a great actual point to say, what is sig hash?
So sighash. So earlier I was ranting about how there's an actual transaction that you want to sign, and then the signature itself is a separate thing as an authorization, right? So there's an actual transaction you want to sign, and of course this is the kind of thing that engineers have to worry about, but most like users, you don't have to care about this. But basically, when we say in quotes sign the transaction, we have a very vague idea in our head of what that means. The transaction itself consists of some inputs and some outputs, right? Certain amounts, and of course the inputs have to reference where this money is coming from, and the outputs have to reference the address, let's say, the amount the money is going to. So that's a set of data, and you want to sign that data. So when we say sig hashing, it's just short for signature hashing. And why does the term hashing come in when I'm talking about signing all the time? Well, traditionally in cryptography, when we talk about a digital signature scheme, we're using some fancy dark arts mathematics, and we're applying it to some piece of text like, my name is Waxwing.
It's a meat grinder. It's a one-way meat grinder.
No, but that's the hashing part. But hang on. So when we say a digital signature, we're saying, okay, I'm signing some piece of text, right? And we have in our head, because we've done it in the real world signing, we have maybe a piece of paper with a bunch of text written down on it, and we're signing it, right? So in cryptography, in a digital signature scheme, we obviously have to encode that statement, for example, I am Waxwing, into a string. So it's literally a string of bytes. And the problem, of course, then gets a bit messy is, well, if the mathematics, the dark arts mathematics of your signature scheme requires that what goes in as a message is, let's say, 32 bytes long, then I can't sign like a whole page of text, because a whole page of text might be several hundred bytes or several thousand bytes long. So the trivial solution is we use, as you correctly pointed out, a one-way function or a hashing function that takes any arbitrary or almost arbitrarily large length of text and compresses it down to a single hash function, just as we were earlier talking about TXIDs and how they watermark and they define the input data. So here, in signing a message, I have to, or by tradition anyway, we have to compress it down using a hash function. So we have a fixed length string, and we put that into this dark arts mathematics technique and put out a signature.
So it's essentially a fingerprint. That's all it is. Like you don't have to show in person your whole meat bag. You're just showing your fingerprint, right?
Yeah.
Like, a signature is a very large thing. All we want to do is just show a fingerprint that signature happened.
No. You don't mean the signature is a large thing. You mean like the transaction can be a large thing.
Exactly. Yes.
Yeah, the message we're signing
can
be a large
signed message.
Yeah. The message to be signed can be a very large thing.
Yes.
We give, instead of signing the whole thing, we sign a fingerprint of it, which is this hash function. So when we say sig hashing, we mean the process by which we take the transaction and turn it into such a fingerprint or such a small piece of text that a signing algorithm can use.
It's funny with our little tangent here on sighash that had to happen. I kind of lost track.
I'm sure Andrew knows where we're going next.
Andrew, where did you stop?
Save us.
We were talking about the discount.
Well, quadratic sig hashing,
right?
yeah.
Yes. Oh, yes.
Quadratic sig hashing, and then somehow that feeds in. And then I also asked, could we have done that without SegWit? And the answer was kind of yes, we could have. But then you were going to say something else. Yeah.
That's right. Yeah. Oh, yeah. I was just going to say, like, in principle, we could have just replaced the check sig operator with or added a new one or soft forked in a new opcode. And then, so here's where it gets scary. You'd kind of have to get rid of the old one, or at least say like the old one couldn't be used in whatever extra block space you were adding somehow.
Well, because we're trying to solve the quadratic sig hashing problem, so we can't leave it in, is what you're saying.
Yeah, right. So, or if we left it in, it would have to be like some sort of second-class citizen that could only be used in a small amount.
Why would you leave it in? Oh, because you want a soft fork.
So I'm moving the two of you on. Okay. We didn't go in that direction. So I know it's super interesting, but we're going to lose them here, guys.
Yeah.
So, okay, how do we calculate the weight? Like, how do we actually do this?
But wait, did we complete? Did we give a general justification for why there's a discount?
Oh, yes,
I don't think we quite got onto that. Before we get the actual numbers, why is there a discount for the witness?
Yeah, so like I think we did, like, because the point is, like, if we get too deep, then it's kind of, it's people can go read the paper. Right? Like,
well, yeah, but I think this is maybe the most common question when I discuss. But I've literally given presentations about SegWit. People talk about this, like this. What is this discount? Why is it 1/4? What is actually going on here? It's really important, I think.
Yeah, that's what I'm saying. Like, people want to know, how is this calculated? Like, why? Yeah. How? Andrew, do you want to try to stab at it? Like, how do we actually calculate the weight?
Sure. Yeah, that is a good question. And yeah, I think Waxwing, we're probably talking about the same thing here. So we're trying to add this extra data that like doesn't go into the TXID. It's kind of this bonus area, right, in a block. And that's how we're going to increase the block size, by saying like all of the old TXID stuff continues to be like a 1 meg block, but then we have this extra data field, and we're going to move the signatures out of the old area into the new area. So, old nodes are not going to see the signatures. But now we've got this new area. And the way that we're increasing the block size is by adding this new area. And so what will naturally happen is you got to look at the kind of like, what are the relative sizes here, right? If we want, we definitely have a 1 meg kind of old area, right? That's fixed, that's consensus. I guess we could shrink it, but like if you try to increase it, that's a hard fork, right? And so if you try to add an extra megabyte, then you've got a meg of old data and a meg of new data. If you try to add 3 extra megabytes, you've got a meg of old data and you've got 3 megs of new data. And now what this means, if you do that, and so that seems like, okay, this is trivial, right? You could kind of set it to whatever you want. If you want a 10 meg block, then you can add 9 megs of extra space. But what's happening is, as you're adjusting your block size target, you're adjusting also proportionally how much of the block is this extra witness data and how much of the block is the normative transaction data. And because the way that transaction fees are kind of weighted is in fees. So it used to be fee per byte. Now we say fee per weight. But basically, it's the amount of fees you pay divided by the amount of block space you take, really is what it is. And so with the block space, we're like 90% witness data. that would mean that every byte of witness data kind of like within a 9 times bigger space, and therefore was costing you 1/9 as much proportionally. And so that's what happened with SegWit, and then the ratio wound up being 3-to-1, right? So we have 3 megs of witness data, and this is all right. We have up to 1 meg of normal data, and then 4 megs, whatever that little bit. So if you have, in principle, you could have like almost no normative transaction data, and you've actually got 4 megs, right? So the constant is 4, it's not 3.
Is this how you avoid the second knapsack problem? Because like you can't optimize to it because you don't know.
Bingo. Yeah. So here's the problem. Here's the reason that we did this weird thing where we really, really wanted to have one metric. It used to be fee per byte. Now it's fee per weight, whatever. We really want just one metric that you can order transactions by. So you might think that you could kind of independently put a weight on this. You can say, well, this transaction is paying, X amount of fee for these, for the normative transaction, and this amount of fee for witness. You could even have like 2 different fee fields, and the user chooses a proportionality or whatever. Like you could really directly make the user pay different things, and like even I guess have a rule that like part of the witness fee has, I don't know, somehow you can make it
essentially become like impossible UX.
Yeah, it would be impossible UX for a user, first of all, trying to figure out these fees. But maybe more importantly, depending on your perspective, for block creators, right? So for miners trying to assemble transaction into a block, right? They want to be able to look at the mempool, have like a well-ordered, say, I want this, and okay, these didn't make the cut. You want there to be a cut, right? You just go until you're full, and then the rest will have to go to the next block. As soon as you have 2 different metrics for costing transactions, you have what's called a multi-dimensional optimization problem, or a multi-dimensional knapsack problem, or maybe it is a knapsack problem as soon as you have more than one thing that you're measuring. And this goes from being something that's super straightforward, right? You put them in order and you just like keep going until you're done, right? That's an ON algorithm, to an algorithm that's NP complete, which means that we don't really know how to do it in sub-exponential complexity. Like it's just the more transaction you have, like it just quickly blows up and becomes intractable, unless something astonishing happens in the world of theoretical computer science, in which case you won't hear from me again if that happens.
So essentially, like we have a problem that we can't solve, right? If we go on that direction. Yeah,
exactly. It's tractable, right? If we can stick it all into one metric, right? By just saying fee per weight, we define the weight to just kind of be proportional to, this amount of the block is witness, this amount is not. That's what you got to pay for, is this kind of like weighted average of the bytes that are in your block.
Yeah. So miners have this issue. They have their, I like to use like buckets or swimming pools as the block building process, right? And we're going to get to that because of the JPEGs later. So the transactions have, like, say, an economic density. They want to have the most amount of economic density in there for fees because that's how they get paid the most. And they want to build their blocks. And we are giving them less money for transactions that have more witness, essentially data, right? Because that witness data is less important for the Bitcoin security long term. It's like I'm oversimplifying, but it's just so people sort of like get the dynamic that we're trying to incentivize here, right? It's like long-term security for Bitcoin, most amount of throughput of transactions, better UTXO management on those transactions, with like more comprehensive scripting on those transactions, because the scripts could be technically thrown out.
Can I emphasize the inputs and outputs thing? Because I think that starts to get interesting there. Like, actually, before I make my point, I want to use a sort of teacher technique. I want to suggest to people, like, here's a concept check question, right? First, the simple one: are outputs of transactions. So outputs consist of, it goes to a certain address and it pays 1 Bitcoin. It goes to another address, it pays 0.5 Bitcoin. Are the outputs part of the witness or not? That's an easy one. I hope if you listen so far, that should be easy. Are outputs part of the witness? Okay, and drum roll, the answer is no, they're not part of the witness, right? Because they're part of the semantics of the transaction. They're part of what defines the money is going from here to there. So that is definitely not part of the witness. But here's a subtle sort of extra question that tacks onto that is, you may or may not have heard of confidential transactions. The idea of confidential transactions is we're going to blind all the amounts. We're going to make all the amounts in transactions be obscured cryptographically so you can't see them. So it's really cool for privacy. It exists in various blockchains, including certain ones relevant to people here. But let's not get into that. Let's not get into that. But anyway, I want to ask a second, more difficult concept check question, which is this. In confidential transactions, it's necessary to have a little addendum, a little cryptographic proof that all the amounts are, so to speak, correct, that they're balanced. So you don't see the amounts, but you have to have a little proof that the amounts actually could be quite big.
It's a fingerprint of the total of that transaction.
Exactly, that's a good way of putting it. It's a fingerprint of the total of the transaction, but it's cryptographic. It's just a bunch of data. Would that be witness or not? That's my second concept check question. And now I'm going to ask Andrew whether it is witness or not in the blockchain that he has worked on.
So, the blockchain that I have worked on is the Elements blockchain for Liquid.
Right.
Yeah, and there it is. It is indeed.
It is witness.
Yeah, it was not very early on.
Oh, did it say I'm not being? That's interesting.
So this is kind of an interesting. So SegWit actually originates with the Elements blockchain, believe it or not. So back in the real 2015, this is the correct order. We kind of came up with a scheme. We knew we had to segregate. We wanted to split apart the witnesses for all the reasons that we've talked about. But we only knew how to do it as a hard fork, right? And we figured, well, we're making a whole new blockchain, so we can go ahead and do it. So we did this kind of crappy version of SegWit in alongside confidential transactions, alongside OptCSV, also originates in Elements, alongside a few other improvements. There's an opt-deterministic random, that we've never figured out a use for, but we added a whole pile of stuff, and some of them turned out to be great, and some of those wound up in Bitcoin. So then we implemented SegWit and we implemented CT, and I think we weren't thinking so clearly initially, and we just went ahead because we were thinking of witnesses like as being signatures. So witnesses are attached to the input.
Yeah.
So, and then later when we brought in, so SegWit showed up on Elements Alpha, and then Luke figured out how to soft fork it, and then we started working on Bitcoin. That's just sort of the history of things on Elements, right? So we come up with them and they're kind of crappy, and then we make somebody else maintain them while we go work on Bitcoin. That's Blockstream research. That's our motto. And then we got this much better version of SegWit from the Bitcoin community. We brought that in, and when we brought that in, we said, okay, let's just stick witnesses on the outputs. So now there is such a thing as an input witness and an output witness.
Yeah. So basically, Blockstream failed my concept check question at the start, but they eventually got it right. Yeah.
Yep.
No, actually, it's funny. The funny thing is, I remember talking on IRC to CEPA and probably you at the time, the years of 2015, trying to understand CT, and it might be 2016 or something. I was like, but hang on, is this? I didn't. I think one of you told me that it was witness, and I was like, oh my god, really? Because in the early days, I think a lot of us just really struggle to understand what this whole SegWit thing is. And I also want to really emphasize another point that Andrew did say, but I really want to emphasize it to listeners is the incredibly important thing that SegWit does is this thing about chaining unconfirmed transactions, because it makes off-chain protocols possible. It's not just Lightning. Obviously, Lightning is the most important one, but there's so many other things that are almost impossible to do unless you can rely on the TXID not changing. And so if you care at all about the future of Bitcoin involving off-chain transactions, and I think you should, because it doesn't scale on-chain. It can't possibly scale.
It's actually impossible.
Yeah,
I mean, just imagine trying to put 8 billion people's coffees on 4 megabytes.
Exactly. I mean, it's just ridiculous. So really, you should have that clear in your head, I think, that SegWit is not just some weird, geeky, technical thing and we're arguing about discount this and discount that. No, it's the only thing that makes Bitcoin even remotely conceivable as the base of a consumer financial network. It itself is not a consumer financial network, as I ranted last time as well.
Yes. So, I apologize to the two of you because it's super interesting. I'm just trying to bring it back because I don't want to lose
but also
I don't want to lose the train of thought.
Inputs and outputs, the balance between them, SegWit changes it. I wonder if Andrew, he looks to be maybe busy, but I'm thinking the balance between them is interesting because it changes the cost of spending inputs relative to spending outputs. Yes. And the UTXO set, perhaps Rodolfo, you could talk about this. Why is the UTXO set so critical in terms of being a user of Bitcoin, or what do you think?
Well, I mean, the whole point of Bitcoin is that it can self-validate things, right? In a human sort of way. So if you have a copy of a valid UTXO set that everybody agrees, right? You have a source of truth. Even if things break, even if the comms are bad. So we can never overcomplicate the UTXO set. And Bitcoin is the only one of the successful sort of cryptocurrencies that has a UTXO set, right? Like Ethereum has accounts. So like you can't fucking trust anything. And then you have like all these smart contracts that have to be actually ran or like so that you can actually have an account of it. They actually cannot account their unit of account. It is really that bad. Right?
Oh, you mean they can't verify the scan TX outset thing that we have?
No, they can't, right? Because they have to do the accounts, and then they have to do all the smart contracts, and then they also and the amount of data is just absolutely ginormous, and then the computation you need for that, and then nobody has a copy of the whole damn thing.
The thing is, even if you could perfectly account for the amount of Ethereum there are today, you have no idea how many they're going to be in 2 years, right?
Yeah, exactly. Right.
That changes all the time. I mean,
and then there is that, right? Like, code is law until they decide to change everything. But going back to this, like, this is as an integral part of the Bitcoin concept. Is this idea that you have this ledger that is very specific, right? It has this linking between where did the first money start and where that money went, right? And then like, because nobody actually has Bitcoin, people just have a claim on that UTXO that exists on the ledger already. So the money already exists.
Yeah, it's not be your own bank. It's everyone else's your bank.
Exactly.
you just happen to have the key. You just happen to have the key to the deposit box. Everyone is
exactly.
Your bank.
You just get to say that yes, I authorize that role to go from there to there, right? And that's really like it's like that. It's so beautiful that way, right? Like how Bitcoin really makes that super simple. And all this crazy galaxy brain cryptographers sort of like try to do every possible change and tweak and improvement without messing that up. And it's like, it's almost like the insanity of the necessity of this, the solutions are so necessarily insane because you cannot change this very simple original concept, right? Like that's the true sort of like, you're really bounded by this, right? You can't just go, oh, we're just gonna fucking like soft fork Bitcoin and do this other thing. You can't do that like they do in these other test networks. Let's put it this way. In Bitcoin, we can't fuck that up. So when you do create solutions, they have to really like take this into account. And we always end up at this like very weird places where like essentially new ground has to be broken. It's all new ground. So anyways.
So about outputs and UTXOs, right?
Exactly.
So what maybe Andrew, you could, I don't know if it's clear in your mind or you've thought about it at all, but this thing about, does it incentivize cleaning up the UTXO set, SegWit? Is that a reasonable thing to say at all?
It does. Yeah, so it means basically with SegWit, you can think of it as there's kind of more cost in creating a UTXO than in spending it. And that's not, it doesn't quite balance out. For certain kinds of output types, I think it actually winds up balancing out. And this is all like, it's interesting to talk about like doing this deliberately to like discount proportionally to the relative value and stuff. Because I think it was almost a lucky accident that like, in order to have a single metric, while adding block space, we were forced to have some sort of discount, and like our target block size happened to imply a certain discount that roughly intuitively matched all these other, different things.
Wait, your target block size? Well, that was such a controversial point. I remember there being about 5
I should not have said that. Nobody I talked to ever talked about a target block size.
Yeah, it wasn't like some cabal in the background said we want to aim for 4 or something.
It was widely understood that 1 meg was too small and 10 meg was too big, say. Right.
Well, that Satoshi did try 32 megs. That was very short-lived. I mean, people were using the day's computational capacity. Personally, I never liked the increase in block size. I wish we had just done the discount within the 1 megabyte total maximum point, but that's, water under the bridge. There's no point in even sort of addressing that. We're not going to make the block size.
But it is water under the bridge, but it is the thing that people are going to want to hear, like, from us talking about, like, 4 megabytes. I mean, do you remember that there was several? There was a 2 megabyte proposal.
Yeah. There was the
8 megabyte
and the
was
16.
The big one. Yeah. I seem to remember Adam Back being really behind the 8 megabytes or something. I don't know. There was
I don't think Adam was. I think Adam was a small blocker on the
sure. Maybe I'm wrong. Whatever, it doesn't matter. The point is there were lots of different opinions. That's the main point.
And people were also just exploring, right? I mean, like, it's not like that people were sort of like forcing this or whatever, aside from the SegWit 2X people, which was the 8 megabyte block people. the cabal of companies.
Oh,
that was an actual
later,
cabal.
yeah. That was the actual cabal. Yeah, that was the real
circling back, right? So the result of this discount and just the nature of witness data is that you have the relative cost to create an output versus spending one. And outputs are inherently much smaller than spends, right? So an output in Bitcoin is more or less a reserialization of the amount. Of the address. You stick an amount, so there's 8 extra bytes for the amount, and there's a couple bytes of length encoding or whatever. But you more or less just reserialize the address, which is pretty small, right? It winds up being, for some legacy addresses, it's like 20 bytes plus 8 for the amount plus 4 of noise or whatever. That 20 becomes 32 for certain script baked witness script hash outputs and Taproot outputs and stuff. But it's still pretty small, right? We're talking in total 40 to 45 bytes, right? Max. And a signature by itself is going to be 64 at least. And then you've also got to do the TXID and index.
Well, in those days, it was 72, wasn't it? It wasn't.
That's true. Yeah, that's a good point. Yeah, so the signature is 72 plus an extra byte, but then you've got 40 almost for, you do have 40. You've got the 32-byte TXID. You've got the index of which output of the old transaction you've got. And you've got something called the sequence number. So it's 40 bytes of noise on top of your signature. So you divide that by 4, and it winds up being really close. And I don't know if this was on purpose, that SegWit it used to be much more expensive to spend an output than it was to create. And then with SegWit, at least for normal single signature outputs, it became roughly on par. And then if you've got a big script and
oh, that's an interesting calculation. I'd never heard that. That actually makes that appeals to a mathematician's brain. Let's have some seriously, have some symmetry between the two, because you want a steady state where there's an equilibrium. So you probably want the input and output costs to be about the same.
Yeah,
I'm guessing.
Was it on purpose?
I can't remember if I bump into this on the Bitcoin Talk or not. Or if it's just from my head. It's way too long ago, but I actually prefer the incentive of the spend being more expensive than the earn. And that's just because of the incentives, right? Is there's this idea that to receive should be cheap. Also, because you may be involuntarily receiving too, you don't control how how the inputs come to you either, right? A receive is a very passive sort of action, right? Or inaction, however you want to see it. So being cheap is important, where the spend now is under your control, is deliberate, and you can also choose the timing, ideally. and it's okay to have the dynamic. Well, at least never have the opposite dynamic, which is more expensive to receive than it is to spend. Yeah. The equilibrium at least feels fair. It's not neither there nor here, in my view.
Can I just clarify though? If input is 40 non-witness and 64 or 72 witness, isn't that either 56 or 58 compared to 40 to 43? Isn't it bigger? Because if the input has just a signature, that would, let's say 72 or 64 divided by 4, right?
I think
you're
talking
right. 16 to 18. So 56 compared. So I think actually, Rodolfo, what you want is true. It is slightly more expensive to.
Yeah, I think it is.
It should be.
Yeah,
but it's marginal, right? I mean, it's we're sort of
it's pretty close,
we're splitting hairs, right?
It's pretty close, yeah. I still don't really know why it's a 4. I mean, I saw some graph sometime. Did you remember that blog post that had a graph that tried to justify the 4 factor by having it in a minimum of some curve or something? I
seem to remember.
Yeah, it was.
It's one of those fascinating things. Till today, and still after today, it seems that I would never get an ultra clear answer on this one. Yeah. It just seems to be a lot of things in Bitcoin are just magical numbers. For people that don't know what magical numbers in programming are, wow, I just picked that number and kind of just perfect. It's the 21 million.
But that's exactly why my mathematician's brain is very appealing to see something where there's a symmetry there, because it removes that issue of having these magic numbers. Yeah. If things balance, actually, it sounds like the factor of 4 probably, as you say, Andrew, is sort of close to balancing it, but maybe slightly favoring.
Yeah, I think 5 would have been too much.
5 would have been too much, and 3 would have been too little. Maybe it's like that, Maybe it's roughly balanced.
Okay. So I think that sort of this is as far as us not starting to draw on boards here, we'll get into the reasons of why the discount is the number that it is, right?
Yeah.
So I guess maybe we can start sort of exploring now Taproot, Schnoor, it's very esoteric for a lot of people. I mean, many people probably never heard of this shit before I came to Bitcoin. You know, I'll just speak like for a second of just like my interest on this. I always felt that because ECDSA doesn't have a proof, and if there is like a very obscure attack on it, or it's found an attack on it, it would never be sort of like the way that the fudsters on cryptographer talk about, like, oh, and then all the keys are broken kind of thing, right? Like, and all the airplanes fall off the sky. No, it's more like, you know, if the stars align in a certain way, or if you build a client in a certain way, you can probably sort of like pick off a few keys here and there, and you can make yourself very rich, right? Or you can, you know, be a state actor that targets like specific victims, right? Because again, you know, we don't have a formal proof, even though it's very difficult, whatever, it's not impossible. Now, Schnoor was under a patent block, right? And so it was not available when Bitcoin was created. And, you know, as much as to me, adding Schnoor is sort of like almost like it's not Bitcoin anymore because it does change like some true fundamental principle primitive from Bitcoin. To me, it was important to have a second cryptographic primitive inside Bitcoin already in it, so that if we do find ourselves in a hole in the future, we had a place to migrate to, you know, with some very shitty way of doing it. Like everybody just moves you to this, and we all agree that this is the block, or whatever, right? Like there's some weird way we coordinate and do it, but at least it's there, right? We have the second primitive in there. It's one that has a proof, and maybe you guys can sort of like give a little bit of like a very short mathematician explanation of like, you know, why it's important to have a proof. So let's address Schnoor first, and then we can get into what you can do with it.
Yeah. So on the proof point, the best way to put it is it has what's called a security reduction. So it's the way to look at it is that when you're using a Schnoor signature, there's this weird kind of backwards logic in cryptography that says that, well, we don't know if you can break it, but if you can break it, you can break this other thing as well. And we think you can't break that other thing, therefore we think it's okay. See, the problem is that all of this is built on this completely, I don't want to say shaky foundation, but it's like very kind of unclear foundation, which is that there are certain problems that cryptographers assume are sort of too hard to break with, let's just put it in layman terms, too hard to break with everyday real computers in the real world, or all of them. You know, they're just enormously hard. So one of them is the elliptic curve discrete logarithm problem. So discrete logarithm is, you know, you're given a point, or you're given a public key, can you find the private key? Basically, that's what the discrete logarithm problem is. And so the idea with the Schnoor having a proof is just that you can show that if you can forge a Schnoor signature, just very, very crude description, if you can forge a Schnoor signature, you can break a discrete logarithm and you can find somebody's private key. So that's the theory. Now, does ECDSA have that? You're right to say that it does not have that because it has some certain, well, fairly significant quirks in the way that the mathematical construction is put together. As far as we know, it's like a lot of that is just to avoid the pattern originally, because in 92, when that standard was set, I mean, Schnoor was agitating for, you know, fuck you all, give me lots of money, or you're not getting my equation. My equation that consists of S equals K plus EX is apparently something that not anyone else is allowed to use. So nice work, Mr. Schnoor, who apparently is still alive. But anyway, and fudding RSA, by the way, with a bunch of nonsense. From what I can tell, a bunch of nonsense, but we won't get into that. So ECDSA not having a proof is sort of true in a vague sense, but... And there's certainly plenty to be suspicious about it with, but there's been a lot of work, hasn't there? I'm sure Andrew can attest to this, like people like Yannick Surin and lots of other people worked on ECDSA. And there's all kinds of weird models, and they kind of half have a security reduction.
Yeah, so there are proofs in these weird models, right? Where you treat weird R computation, you say, well, what if that was a random oracle, even though it's got like tons of algebraic structure? It's just right. Yeah.
But you know, for the grug brain, right? I mean, like it's fantastic. It's
I don't think the grug brain is listening to your podcast.
No, they are like they're like people. It's kind of cool. Like I mean, and this is why I keep on always trying to bring it back to a bit of the grug brain. It's like you know, people get the concepts. Like people really do. It's just if we take the time and we sort of like get people there, people get there. It's kind of fascinating. So anyways, so we have Schnoor. Schnoor is really cool. One of the things that you can do with it that you can't do with CDSA, at least like you can do it practically, is you can add signatures instead of multiplying them, right? So now you can have much smaller things, and smaller things are always better when it comes to data, right? Because now instead of having a very big transaction bytes wise, right, which costs money in Bitcoin, you have a much smaller thing, so you can have even more signatures. And the signatures, it can get complicated, but they can have like different weights on how much they influence the truthness of the total approval of that transaction, right? And that gets us to Taproot.
Yeah. So I guess to tweak what you said a little bit, with Schnoor signatures, you can add multiple signatures together, in a way that mathematically looks a lot like you just add two signatures and you get like a sum, which is just like the same size. Whereas with ECDSA, you kind of have to concatenate them. Like there's not a notion of multi, you just got to put one after the other. And so you can do multi-signatures this way with Schnoor, where you have multiple parties who like all collaborate to produce a single signature. And you can do threshold signatures, where you have like a whole bunch of parties and only certain members of them. And you can add weights, as you were saying, where like some parties, their signatures count for 2 and so on. You can do all this. It's harder in practice than I think we realized. Like we knew this has been like a folklore like pretty much since like 1990. There's been kind of folklore that you could do stuff like this. And there are published papers about doing it from the mid-2000s. And it turns out they're just like wrong in practice, right? In practice, it's quite difficult. You got to be careful in how you combine the keys. And like if people choose their keys in malicious ways, certain bad things happen. And if people like do this interactive thing and they send inconsistent data to each other, bad things happen and blah, blah, blah. So there's a whole lot of technical work that went into this. But with ECDSA, it was even worse, like significantly worse. And a few people went ahead and implemented like various multi-signature schemes for ECDSA and stuff. And I would suggest this is just like really reckless, right? Like the amount of crypto code is so much, it's just an enormous amount of complexity and additional assumptions, right? So Waxman was talking about how when we say a proof, we really mean a reduction, right? If you can break Schnoor, you can solve the discrete log problem. Well, if you can break a Schnoor multi-signature, you can solve the discrete log problem. If you can break ECDSA and these weird models, you can solve the discrete log problem. If you can break confidential transactions, you can solve this. It's always the same problem, right? Either you're solving this discrete log thing or you're breaking the SHA-2 hash function in some way. With multi-signature ECDSA, there's other things. There's like, well, if you could break this multi-signature ECDSA thing, then like maybe you could solve this weird variant of RSA called palliate, which is this form of homomorphic encryption. And it makes you less comfortable as a cryptographer to say like, well, there are multiple impossible things and people only have to pick one of the impossible things now instead of this one.
Well, it also creates a problem with all the implementation problems too, right? I mean, maybe you broke something, but you really didn't because the implementation on how that was constructed was crap.
Yeah.
And you thought it was perfect. So technically you didn't really break the encryption. You just broke, you just produced something that was not very secure. Yeah,
absolutely. Right. Yeah. This is not, as a cryptographer, right, I like to think that people will like break the mathematics or find a flaw in the math. But in real life, like actually implementing all of this stuff, every little piece of thing has all these caveats. And the more of those you have, the greater. So
can I just be a nerd for a minute and just say, isn't it the one more discrete log on Musig too, not the discrete log?
Yes, in the original proof, it was one more discrete log. The last time I was actively working on it.
Yeah, it keeps changing. Right, it changed so many times. It's true. They're difficult to keep up. Yeah. Anyway, it doesn't matter. Yeah. It's basically the same kind of thing. Anyway.
I think it is, but I've got to look that one up.
Yeah, you'd have to check. Yeah.
Speaking of looking earlier, when it looked like I was busy, I was trying to figure out the witness thing, where the range proofs in the witness, and I couldn't tell. I was reading the alpha code. And
you were looking at the code, yeah.
Yeah, right. It's twisted up. I couldn't tell. So Schnoor signatures. When I first started like doing Bitcoin research, so I showed up in 2011 or so, just like fooling around with Bitcoin and like sending it to people and saying like Ron Paul revolution and like kind of parading around and stuff. But it wasn't until 2013 that I started like looking into how did Bitcoin actually work and like what was I even doing here and stuff. And in that, like the very first thing that I did, was like investigating Schnoor signatures, right? So Schnoor signatures we've wanted forever and ever and ever, and we considered sticking them into SegWit actually, but SegWit was already like several different components that were pretty controversial, and also the peer-to-peer network upgrade. Like ironically, because this is like to the general public, this is a bit obscure, right? We think of SegWit as a consensus update. We had this extra block space and stuff, but by far, like probably 90% of the complexity of SegWit was making sure the peer-to-peer network did not like segment and like have peers banning each other because they didn't recognize like some future thing or some past thing or whatever. Just getting the peer-to-peer network to be resilient was all of the complexity. So we didn't want to stick any other stuff in. So we didn't throw Schnoor in, we didn't throw opcat in, we didn't re-enable the multiplication opcodes. We didn't, we had this like giant wish list, right? You ask 10 Bitcoin developers, we got 1,000 different things that they want in there. No, SegWit didn't. So
can I just ask about that, about the peer-to-peer? Because as far as I'm aware, the trick was that by using what do they call the flag and marker bytes or something, the old nodes that weren't updated would immediately see it as in the block as invalid. Not the block, the transaction or the block. I'm confused now myself. But if there's a transaction message, it wouldn't be valid because it has this marker byte, which like it shouldn't be 0, but it's actually 0.
That's right.
They just get rid of it.
That's right. So the way that we stuck it in is we set that it was actually the number of inputs. We set to 0.
Yes, the number of inputs 0. Yeah, exactly.
And so SegWit nodes, we say, if the number of inputs 0, well, the real number of inputs is the next byte, and there's witnesses after, right? So exactly. Old nodes would be just like something weird is happening. And so you have to make sure if you're talking to a pre-SegWit node, you have to make sure you use the old style encoding is kind of the solution to that.
That's the trick, to use the old style encoding. So you had to know which kind of node you were talking to.
Yeah. So
which is awkward.
So we wanted Schnoor signatures forever and ever, like long, like before SegWit was even like a twinkle in whoever's eye. We wanted Schnoor signatures. And Taproot was really kind of a miraculous thing where we were solving like 5 different questions. Actually, before we move on to Taproot, should we talk at all about ASIC Boost or any of the controversial, no?
I kind of do just because of my own personal thing, but like, you know what, maybe we should just move on.
All right, cool. Well, let me say like a second thing.
We're thinking forward. Yeah. We're thinking forward.
There we go. So SegWit was like such a wonderful change that we thought nobody's ever going to like. This will be not controversial at all. We gave it this complicated name, segregated witness, that no one would be able to remember and stuff. And then as it turned out, it tread on some commercial applications, which caused there to be a lot of motivation to fight against it. Right. So
we fucked to the bad people, and they lost.
There. All right. There we go. That's right. Yeah. We're just like in the comics, and So with Taproot, there was a bit of apprehension because it was like kind of exactly the same story. We're like, wow, we stumble into this thing that like fixes like 20 different problems we had and makes nothing worse. Like surely no one will get mad about this. And then ironically, like the kind of like ridiculous infighting about how do we deploy Taproot in a way that like won't cause some bad actor to do bad things. Like there was all this fighting about that, and it almost didn't get off the ground. And then finally, there's this speedy trial thing. We're like, well, what if we just do it, and if nobody complains, then it is, and then nobody complained. So sorry. So with Taproot,
we can get into speedy trial maybe at the end if we still have time, because it's a fascinating dynamic too.
Let me back up and talk about Taproot. Which again, I'm going to bring everything back to elements. So there's a cool crypto trick. Oh, and also what you were saying earlier about how in Bitcoin, everything has to keep working, right? Like you don't...
Backwards compatibility is the kind of whole point.
Backwards compatibility, and you can't hard fork, you can barely soft fork. Like you really if you can figure out how to do some sort of crypto with the existing things in Bitcoin. So I gave this talk at NIST, the National Institute of Standards and Technology in the US, like outside of Washington, DC and stuff, to all these like normal cryptographers who were doing like normal crypto and standards and stuff. And I was describing... And they let me give a keynote talk just about the way that Bitcoin cryptographers think. And the whole time, and I got like laughs from these groups, right? Because I would show them the kind of shit I was doing. Where I say, this is a signature nonce, right? Here's, it's an R and an S. Here's a nonce. Here's all this stuff that we figured out how to stick into the nonce because we couldn't change the signature at all. So we just like built these like incredible novel crypto systems and like kind of rammed them into a signature nonce. So this is classic Bitcoin crypto. So this is classic Bitcoin crypto, what I'm about to say.
We're talking about adapters, right?
Yes, adapter signatures, but also like signed a contract and paid a contract.
Oh yeah. Signed a contract,
This is a lot of fun. I managed to do an entire like 45-minute talk like of detailed like shit that we stuck into signatures without changing signatures. Taproot is one of them. So elements. In elements, it's a side chain, which means you can move Bitcoin over, you can move Bitcoin back kind of thing. So what you do to move coins into the sidechain is you send coins to the what's called the functionary address, which are the custodians of the network, and then on the other blockchain you need to make a claim. You need to somehow prove that you sent them to the. You have to prove two things: that they went to the functionaries and that they belong to you. So can we combine those somehow? And it turns out, yes, there's kind of a cute way to do this, where you can transform the functionary's public key into a commitment to your own public key. And what you do is you take the original public key, right, and you hash that along with your public key or your script or whatever you want, right? And then you get this hash of all these things together. You multiply this by the curve generator, G, to turn it from just a number into a curve point and add it to the public key. And it turns out that provably, assuming your hash function was a legit commitment, if your hash function was a random oracle, then this is a random oracle that commits to the same data, is what you can prove. So you get kind of a public key that's now like, it remains a public key and it remains controlled by the same party, like the same secret key with a tweak, but it's a public tweak. The same secret key will continue to work and stuff, but now it's also a commitment. So what we do to move stuff into Liquid or Elements or whatever is you would commit to your own public key, and then over on the other side you say, oh, here's my public key and here's a signature with it, as though you were spending a normal output. But it's not a normal output. It's actually an output on the Bitcoin blockchain. And rather than being a normal script, it's a script that's embedded inside of a public key of a different script on Bitcoin, right? So
add there, just quickly explain to me what committing means.
Sorry, committing. Committing means that you take some data and you produce a fingerprint that doesn't necessarily identify the original data, or you can't recover the original data necessarily. But if you change your data, it doesn't. The commitment would have to change. So if I said what number am I thinking of between 1 and 10? And you gave a guess, right? Then I would, of course, just change my number after you guess, so you never win it, right? So one way to avoid me cheating, if we wanted to play this number guessing game, is I would send you a commitment. I would take my number.
It's a fingerprint.
Yeah, I would take my number, I'd hash it with some random stuff so you couldn't just try every number, and then give you the hash. And now the hash has committed me. There's no way I can reveal a different number than the original one and still make the hash work out after all said and done. So same principle in Bitcoin, right? When a TX ID is actually a commitment to all of the data. The signature hash is a commitment to all of the transaction data that you're supposed to sign, right? And what that means is that if you change any of that data, the commitment changes and the signature changes and the transaction is not valid anymore, right? So and then when the transactions go into a block, it's a commitment. So if you try to change the transactions in a block, then the block becomes invalid, right? The proof of work is a commitment to the block contents, right? If you change the block at all, the proof of work's invalid, you got to redo it, right? So everywhere in Bitcoin, everything's a commitment. And this is the purpose, is that it kind of anchors some particular data to a 32-byte fingerprint. So we call this pay to contract, was the idea, where you're sending money to someone, you take their public key, you tweak it to commit to something. And the idea behind Taproot was we were kind of speculating, and this was Greg Maxwell and Peter Willett and I. We were at a coffee shop in Mountain View, California. This all was one, and we all had these different problems we were trying to solve. So, if we could make Bitcoin script somehow be better, right? How could we make it better, right? And the one that I was trying to figure out was just if you have a transaction, a claim or refund style transaction, we've got some sort of key or whatever, but then there's a lock time, and then there's a different key after a lock time, right? So your coins are held by some key, but then if they don't move in time, then they're held by a different key. So this pattern is used in Lightning, right? So you've opened a Lightning channel and your counterparty never shows up for, however long, then you can take your coins back, right? Because of lock time, it's claim or refund, right? Pretty much every multi-party protocol. But the thing is, you never use the lock time, right? Your counterparty is there, right? You just need this extra clause so that, there's not an incentive to cause problems. So you're thinking, how can we hide that, right? Ideally, you don't even reveal it, right? Not even about hiding it. You just don't want to encode this extra code, right? That doesn't even ever get used. So you're thinking, and then we're well, often you've got this public key and then this extra clause. So maybe we just stick it into there. So we get a modified checksig opcode, right? Where the public key can alternately reveal a commitment. And then Greg, I think, said, why do we even need an opcode? We just made the whole output be a public key. And that was Taproot, right? And Peter was there. Peter did some shit as well, right? It was kind of a very rapid conversation. And it was kind of cool. I went from 0 to almost the complete Taproot thing. And we realized we could bring in Mast with another idea we wanted to bring in. In general, if you have multiple different branches, multiple different ways the script can be spent, can we make it so you only have to reveal one? Well, yeah, there's this concept called masked, and there's been various proposals, Merkleized abstract syntax tree, where you take all of the things and you just like commit to pairs of them and you build this tree out of that. And then you kind of like just get to reveal one path in the tree. And the rest of them just stay as hashes. Entire like half of the tree is just a single hash. But they were all controversial because like people would argue about the exact encoding and like would we add an opcode and would we blah, blah, blah. And like what are the limits and whatever. And nobody could get any traction. Well, with Taproot, we had a public key and a commitment. And so that commitment didn't have to be to a script. It could be to a tree. And there's like almost no room to bike shed the way this is like, there's just such a small compact thing, right? It just naturally fits and there's no room to bike shed it. We did. We use this weird XOR hash thing so the tree no longer had a left to right ordering. Like all the branches can kind of rotate freely and stuff like that. But for the most part, this gave us kind of a bike shed proof way to bring in masked. It gave us a bike shed proof way. Well, if you were replacing the whole script interpreter, which we kind of were, we got to replace ECGSA with Schnoor, right? So with Taproot, then let me just finish saying what Taproot is, right? So with Taproot, your outputs are just public keys that commit to stuff, okay? And that stuff is some alternate script or whatever. So when you're spending a Taproot coin, you can either just like sign with the key. And remember earlier I said with Schnoor signatures, sign with a key could actually be multiple participants, or it could be a threshold. Or with adapter signatures, sign with a key could actually mean like you're validating a transaction on another blockchain and doing atomic things and like doing lightning channel updates, or like accepting a secret from somebody further along in your channel, reblinding it and passing it to the party behind you, right? Like you can really do some magical stuff just with one signature. Amusingly, right, as always, this came from a lot of work I was doing on the Grin Mimblewimble chain. How can we Mimblewimble only has signatures, right? It has no scripting. It inherently has no signatures. Like, how can we do stuff with just signatures? How can we do scripts? And then, like, I figured it out. I'm like, oh, let's go do it on Bitcoin, and just kind of like wandered away. Never hire me to do stuff for you if you think it could ever be useful for Bitcoin. Just like, as soon as I figure out how to do it for Bitcoin, like I'll lose interest in your stuff.
So now so now we have this like very sort of, we essentially have a way of putting a lot of stuff that we don't want people to know. Yeah. Right. Inside a single key, right? A public key. And that's what the blockchain sees, yep. Right? Like that's what everybody in the chain sees. And you get to decide like how you spend that. And like by essentially revealing which script is spending that.
Yeah. Or if in the happy path, you don't even reveal any script, because sort of by default, Taproot has an implicit script, which basically just says you sign with the key. You just treat the key as a key. Don't even reveal
That's
anything.
A key span.
Yeah, it's a key span, exactly. And, these might be multi-signatures, they might be whatever. The cool thing is the network can't tell. So what this means is that for something like Lightning, say, where you have a 2 of 2 multi-signature on your HTLC outputs, and then you've also got these time lock things where you have to reveal stuff under certain circumstances, right? And if you don't pass the hash through your back channel, then you have to reveal it on chain and blah, blah, blah. But normally, you just have the two of you agree and you can just sign. So you get into this neat situation where, assuming things go well, atomic swaps and Lightning, assuming Lightning was updated, and people are doing that now, called PTLCs, and normal wallet transactions and multi-signatures and thresholds and liquid, so these all look the same to the blockchain. They all look like just a single key and a single signature. And so you get this big privacy benefit where all of a sudden all these things are sharing the same kind of anonymity set. None of these things look remarkable. They're much harder to censor specific applications. You can't really recognize them. And it's also smaller, right? Like now you just have a single key, 33 bytes. But we found a way, Peter found a way to make it 32. There's a byte we saved. 32 byte public key and a 64 byte signature. Again, it used to be 72 plus a sighash byte, but we shortened it down to 64 plus a sighash byte, and then we said, well, actually, no sighash byte means default. Now 64, right? So we were able to get one key, one signature for a huge range of different applications, and we were able to compress both of those things to shave off a few bytes as well. And we added some more upgrade mechanisms. So we did this as a SegWit v1. So SegWit, among other things, introduced a new upgrade mechanism where we would keep the same address type, sort of, and you would just like change 1 byte, and like future nodes who didn't understand this new thing would at least be able to encode and decode addresses and still send us stuff. So we wouldn't have a situation where all the wallets had to implement this new error correction code. Taproot said, well, not only are we going to keep the SegWit, you can update the whole output type. You can be SegWit, or it can be Taproot, or it can be some future thing. And Taproot you've got these branches of different scripts, and all of those have their own version number. So now if we updated the script system, we could have different scripts with different versions, and now nobody can tell kind of what different script versions you support. They can only tell what version you actually use. So you can imagine in the far future, if we had like some sort of Stark thing, or if we had simplicity, or if we had any of these like mega overhauls of Bitcoin script, you could just use, well, hopefully a key spend, but failing that, hopefully the old school Bitcoin script that everybody knows and loves and you know is normal. And only failing that, do you use the crazy new stuff. So you can use the new stuff without marking your outputs ever, right? Like you get this kind of future privacy thing.
I've got a little story that illustrates this point about how cool it is that things get hidden in Taproot. Like I got very excited. You probably don't remember this, Andrew, but years ago I spoke to an IRC and I said, oh, isn't it possible if we use adapters, we could actually have like multi-party atomic locked transactions where it's difficult to describe, but I don't want to get into it now. So I'll give you the story at the high level instead of the low level, right? So, but basically, I wrote this some toy code. I got a couple of friends to do it with me. We collaborated. And what we did was we had 3 people who we all we did an atomic swap, but instead of a 2-party atomic swap, it was a 3-party atomic swap. So I paid, Alice paid Bob, Bob paid Charlie, and Charlie paid Alice. And the cool thing was that in this construction is if any one person ever publishes the transaction paying them, the other people can also claim their funds. And it's always safe like that. Every person is safe from all the other people in the group. So I got like 2 or 3, I got 2 other friends. We did it on, I don't know, it was Telegram or something, and we just coordinated, and we were all running the code, and I broadcast my transaction, and they were able to broadcast their other 2. And I thought, this is cool. I've done this incredible new trick. So I published it on, I think it must have been Mastodon at the time. I wrote a message. I said, look, here's this incredible, nobody else has ever done this before, look. And what did I show? I showed 3 Taproot transactions. Unfortunately, they just look like completely ordinary Taproot transactions because they're just 3, we're just using multi-sig. So Peter Wooler came back to me and he said, are you sure you're the first person who did that? Because it just looks the same as any other transaction. And he said, oh yeah, you're right. Yeah, that's true.
It's kind of the point.
Yeah.
Is the point, right? So no matter how crazy and clever what I'm doing in the background is, nobody sees that. I mean, there's a slight exaggeration, right? Because most of the time what we're talking about is we have some backout paths. And so it's like, if something goes wrong, you still have to publish the backout path, but at least you only have to publish that one single backout path, even if there were 55 different other backout paths. And you do expose a little bit more data because we have the Merkle tree, we have the Merkle proof, and it at least tells someone the depth of the tree. So if I'm using a really complex script with 1,000 different conditions, you're gonna at least know that it's big. But from the point of view of a business, that's already way good enough, right? You know that people can't see all of your policies, that they're only going to see the one policy you executed.
If we bring this back to earth,
that was the down to earth bit.
No, I know. No, but I feel like we haven't sold Taproot to the people who are going to be using Taproot, right? It's one of those things that it's the super galaxy thing that we can do that's super cool. The folks who think about this stuff like you, it's super exciting. But I feel like it hasn't been fully sold to people. What are some very sort of new mundane transactions that people could do? Mind you, right? The complexity of this is very high. So we're still building Moosig too. We're still building all this cool stuff that's going to take full advantage of this. Right. So we're not quite there yet, but we needed this in. So in order to get there. Right. So what are things that people could do maybe now or very soon in their normal sort of lives?
So one thing that comes to mind is you can have a normal wallet. So this is maybe, I'm gonna gloss over some descriptors.
Sure, please gloss.
But here's a concept that you would have liked to do for a long time, right? Is you have your coins are controlled by some sort of key, right? It's just you just got a normal wallet, but you'd like that if the coins don't move for a year or something, that you can recover them with some sort of backup key, right? This is basically so that if you lose your wallet or if you die or something, you can at least switch over from the coins are gone forever to now they're spendable by some low security key that hopefully you still have control over, but maybe you'd give a copy to your lawyer or to your friends or whatever. And then, but prior to Taproot, this was expensive, prior to descriptors and miniscript, it was non-standard and difficult to implement and stuff. But like prior to Taproot, it would actually cost you more fees, right? And it would mark your addresses looking weird, right? So you would be marking yourself as doing something strange. You would be revealing that you had this particular policy where you've got one key and then another kind of thing, and which keys those were. And you'd be spending money to encode all of that extra data on the blockchain. So all of your outputs would have like a bunch of code that said check with this key, or if there's not a valid signature with this key, then check has it been enough time, and is there a signature with this other key kind of thing. And there's all these like extra like if else kind of bytes and going on. And it's costly. You got to put all these extra bytes, especially you've got to put 33 bytes to just encode a stupid public key that you're never going to use in practice. So with Taproot, what you can do is take that backup kind of thing, this backup policy, and you don't need just one. You can actually put like, dozens or millions of them if you want. If you can think of a million different backup keys, and you just put that into your output. So now from normal wallet behavior, and what's kind of cool is that you don't actually even really need to implement the emergency spending, right? Like you can go like hire a wallet author, like when you actually need it kind of thing. All your wallet needs to understand is that this key that it's spending with is tweaked with some script that it doesn't, it's just tweaked somehow to have this backup script. The wallet doesn't need to understand the backup script. The blockchain never sees the backup script, right? Because it just sees a tweaked key, which looks the same as any other key. So you can just basically use a normal wallet with like this tiny bit of extra functionality, which is like allowing the key to be tweaked by an arbitrary thing. And then you just use a normal wallet, but you've got this backup policy.
That's really cool. I'd never heard anyone describe that point, that you can separate out the functionality of the complex backup scripts and like have a wallet that doesn't even know about it. I actually didn't think of that. That's really good. Yeah.
So then what is the gap between, because what we're describing here is almost a covenant, right?
No. Well, it's similar in some ways, right? So a covenant will kind of control where the coins can go. And here I'm saying, well, we're switching over to a different thing, but it's functionally is quite similar, right? You've got a time lock alternate, right? You've got a time locked, some sort of script that kicks in and can redirect the coins if.
So like, I mean, I don't know if maybe it's a bit out of scope, but since we're here, like, why aren't we trying to sort of implement some of these solutions instead of, say, for example, pursuing, say, upvolt, right? I know there's specific differences, but yeah.
Well, there's a very concrete difference actually, which is that upvolt. I mean, it's even from a user point of view, it's much better. So what upvolt lets you do is it lets you choose a destination for your coins. And when you send it there, you aren't allowed to send it directly. You have to send it to the staging area first. And then in the staging area, it is forced to sit. And then after it sat for a day or a week or whatever, then it can only go to the destination you picked initially, right? So it's like guaranteed to go to the right destination, but it has to sit there for a little while. And then while it's sitting there, you have the ability to like claw it back and like reset the timer. Well, forget I said claw it back. You just have the ability to reset the timer. So if somebody steals your coins, the only thing they can do is try to take it, but they're forced to put it in the staging area before they can take it. And during that time, you have the ability to keep resetting the clock on them, so they never get it. So there's two aspects of this. So one feature of this is that you get kind of this backup key kind of situation. So if you lose your keys or they're compromised or whatever.
The nuclear key.
Right.
Yeah, the nuclear option.
Key. And the other thing is if your keys are leaked, like if somebody else has control over your keys, upvolt can still save you. Whereas what I'm saying cannot. And that if you lose your keys, somebody will just spend them immediately, right? And it doesn't matter that if they like were very nice and waited a year, then you could get them back, right? Like they won't. So that's the difference, right? Now, why are people not implementing even this, which is really useful? The reason is I think to implement it properly. So if you're writing homebrew wallets and you're very lazy, like I am, then yes, you will do stuff like adding support to just tweak your key and say, oh, I'll fix it later, right?
I feel so bad for your partner trying to recover your coins.
I have another story. We're running low on time, but I did actually write out an estate planning document on how to recover my coins. And that was a real wake-up call, writing that document.
Yes. I know, because we get the support tickets. We hear from the shadowy supercoder wives trying to recover stuff, and it's always not pretty. And I always say, I know you're smart, but, keep it simple because people will have to recover years later.
Absolutely.
And documentation fades too. It is surprising how much documentation, because people have it in steal their seed, but they won't have it instilled their documentation, right?
Yeah.
So that could burn and it could be lost forever in the entropic space of addresses.
Yeah. So absolutely, I would say if you've got any Bitcoin, you should have talk to an estate lawyer and set up a trust or something for no other purpose than that you have documents that's at your lawyer's office, right? And people know to call the lawyer, right?
Yes. Sorry, that was a tangent. So
I do stuff like this, right? Where I tweak, but a real wallet author is not going to say oh, well, you can tweak it with his backup key, and maybe in a few years, if we're still in business, we'll write some code that will let you recover it, kind of thing, right? If you're a real wallet author, you want to support explicitly support the policy encoded in miniscript and stuff like that, and then we're again into stuff that just takes a long time to write out the specs and takes a long time to implement and stuff. But we're getting there.
Yep. I mean, MooseSig too just sort of had some update recently. I haven't had a chance to look at it, but
BIP 327. So
there you go.
Oh, you got a number, right?
Yeah, there is a BIP number, so that means now people will be more confident implementing things, knowing that it's less likely to change drastically, right?
Exactly. Can I just make a brief point on that? Is to
Please
add into Andrew's a very excellent, interesting example of how it might be useful practically. I think what I'm just waiting for desperately is Lightning implementing Musig 2, because the thing about Taproot is it didn't have SegWit had this massive tailwind, which was this discounted fees at a time when fees were a huge deal. So everybody just piled in. I mean, people were complaining, it's only 20%, 30%, 40% adoption. But it ended up being 80% after a few years, or 90, whatever. So the thing is, Taproot, I mean, at the time it was being activated, I was telling people that there's just no way whatsoever people are going to take this up quickly. It's just not going to happen. And because there's no incentive, right? I mean, basically, if you look at the costing out, it's basically there's a byte here or there. It's basically the same cost for ordinary things, which I think technically it's very slightly more expensive, by 1 byte. So there's no incentive whatsoever. So it's absolutely crucial to me, because I see Taproot as a significant improvement and evolution of using Bitcoin in smart ways. And I think Lightning has got to lead the vanguard there, because once we get the anonymity set of people using it in Lightning, especially Musig 2, but also Taproot generally, especially Musig 2 and the point time lock contract thing, it's going to make people like me who are very interested in finding clever privacy uses for Taproot, let's say, it's going to give us a massive space to work in. At the moment, we don't really have a space to work in, at least not as much. The code tooling isn't there so much. I mean, I implemented Musig myself for this experiment I just described. X-only pub keys were a pain in the neck. It was such a pain. And I know I'm not the only person who had that experience. There's a lot of technical, gory details here that once we get the libraries fully embedded and as you say, that the BIP's out, everyone's writing the code, it's all clear and tested and proper. And then when Lightning does it, that's going to be the touchstone. At that point, people will start using Taproot, in my opinion.
I think a very sort of interesting grug brain part about Taproot is that you can have, you do get a lot more privacy, right? Yep. Because people don't know what you're doing. They don't know if it's a multi-sig, if it's not a multi-sig, if it's single sig. You cannot know. So that's just a small little a free feature that we get out of that.
Not small, it's huge.
But the other thing that I'm really excited about is that Lightning nodes with coins at risk, right, could implement a lot better multi-sig on the coins that are there. We could come up with better ways of having those hot coins being a lot more secure.
Yep. Yeah, you could have multiple hardware wallets, from different brands, for example, that have to cooperate.
That's right. So I guess that leads us to what got us to have a lot of people hating on Taproot, which is the ordinal inscriptions. And I still think that Casey was absolutely brilliant on how he hacked this in. It was very much in the spirit of how we hacked everything into Bitcoin so that everything is backwards compatible, right? And truly leveraging the very core principles of Taproot and the segregated witness, right? There's very few things here that are not brilliant. I mean, we may disagree on I don't like the DJing JPEGs. I think this is a waste of space, but it doesn't matter, right? It's a valid transaction that takes advantage of every single aspect of how Bitcoin is supposed to work, including the same things that defend your tap script. And also gives us a price floor for the block size to the block now. I mean, we don't have to like it, right? But it does that. So maybe do you want to sort of like just sort of like touch a little bit on like the mechanics on how the inscriptions are put there on the script and how they're accessed? And we don't have to get into ordinals. That's sort of like
sure. But just in general. So this, I should say something, because this is kind of doubly my fault that this is possible. But before I say this, though, so as soon as we had the witness discount, right? Like, it was in principle possible to like stick massive JPEGs and stuff into transactions. But there were limits in how long your script could be, and what are called standardness limits, where something's allowed by the blockchain, but like nodes won't propagate it, kind of thing. That meant if you wanted to do this, you'd be forced to kind of split your JPEG across multiple transactions and multiple inputs in a transaction, and it would be really quite a chore to do. And so with Taproot, some people were able to just like cram it all into one input. And so let me talk about the justification for this, right? Which is that with Taproot, we had, as I said, like a whole new script version. We got to swap out Schnoor and stuff. When we were working on Taproot, we were also working on this thing called the mini script, which is this way to like kind of produce different Bitcoin scripts that are very structured in a way that allows you to have different branches and different choices and thresholds and things in a way that a generic wallet could just figure it out. You didn't have to write custom wallet code for everything you were doing. And we also could kind of optimize things, right? So you could say, like, I want like 2 of these 3 keys, or after a certain amount of time, like 3 of these 4 keys, or like this hash preimage, whatever. You can just have this arbitrarily complicated thing. And we had what we called a compiler that would take this policy and convert it into mini script in a way where it would actually be a Bitcoin script that was hyper optimized. And using this, we were able to find a more efficient version of the liquid custody script. We were able to find a more efficient version of HTLCs. We were like, it just turned out like, and these are things like both of those, we spent a lot of time and like really smart people trying to hand optimize these. And then we just wrote this general framework and let it rip. But the problem, let's go way back to talk about multi-dimensional optimization. The problem that our compiler had was that in script, we did not have one fee per weight kind of thing to deal with. We had to think about, well, there's 201 non-push opcodes that you're allowed to do. And the script itself can be at most, X number of bytes. And you can have at most this many items on the stack. And you can have at most 20 sigops, which are check sigs and stuff that you execute. And sigops are counted in some weird ways where, like, I think they count even if they're in an if statement and they don't get executed. And there's all these weird rules. But we had like 5 different metrics that we had to simultaneously constrain ourselves in while we're trying to optimize our kind of core thing, which is just like, how can we use the fewest bytes as possible for our script? And we can't just do that because we have like this like crazy like multi-dimensional awkwardly shaped box. So with Taproot, we said like, screw it, just get rid of all of it. So we left a couple like extreme limits in, right? Like I think your scripts can't be more than like 100 kilobytes or something like that. But for the most part, we got rid of the SIGOP stuff, and we got rid of, and you can only have like almost 1,000 stack. Like we put some limits in place that you kind of can't hit under sane circumstances. But for the most part, we just have one limit, which is how long your script can be. And we have this kind of cute additional thing where rather than having a SIGOP, which has its own independent limit, we say, well, if you use a check sig or something, then you're required to just somehow make your script 50 bytes longer somewhere else. And you always will in practice because you need a signature that's more than 50 bytes. So, it doesn't affect users. But for a validator and for an optimizer, it means you only have one thing to optimize, right? It's a single, like, how many bytes do you have? So as part of getting rid of this, like, absurd, awkwardly shaped hyperdimensional box, we then turned out it allows somebody to just kind of write not if or 0 if, right? And then the rest won't be executed. Like a whole JPEG end if, right? Yeah. Which is very clever. And I think, so now I'm going to be controversial and state my own opinion here, but I think this occurred to us and we kind of shrugged and said, like, if that's really the best thing that, I shouldn't say my feeling is like, if that's really like the fee market is willing to support this kind of like stupid crap. And there's been like, we had Satoshi Dice and we had various other...
Satoshi Dice was one of the first controversies for block use.
Yeah, right.
Remember, they were essentially like spamming, but there is no such thing as spam in Bitcoin because they're paying their fees, right? That is my view.
That's a reasonable view. I would say like if it's shit, it'll go away. Basically, like these things like none of these are sustainable businesses, right? Counterparty was another big controversial one. And so on. And like this particular one, they're using witness data and they're putting it in a part of the script that's not even executed. I mean, that's really like the least obnoxious way you could do this, right?
I mean, it was. He cares.
Can I make a counter?
Yeah, sure. Please do.
I also went through the same reasoning in my head. Like, this is stuff that is trivially, like, let's say, prunable. From the point of view of me as a node runner, I don't know what my software is doing, but I know I can get rid of that, and I don't care about it. But the counter argument to me is, well, yeah, but it's still bandwidth. You can't avoid downloading that.
Yeah, you can't.
But here's the thing, right? Like, I rather was the JPEG people that showed us this sort of like a bandwidth attack on Bitcoin, let's put it this way, than it was some state actor doing some other really bad shit.
But I mean, who gives a shit who he is? But what do we do about it? Let's say actually.
No, but you can't. You can't do anything. How about this? I'll state my view here.
What if you
hang on. See, so I did a 2 hour with him, and I actually did a 15-minute cope where I go through every single stage of grief in the thing. So the problem is this, right? It's all the same principles that help the useful, between quotes, scripts helped his JPEGs, right? If you try to prune your node or build filters and try to get a lot of people to do it, and most miners don't mine it, all it takes is one miner and one motherfucker with all the JPEGs on Amazon. Okay? Like, that's it. That's all you need to perpetuate this. However, the incentives for miners to mine this where we have empty blocks is super high, for one, right? It could be JPEGs or it could be other data. So people are going to end up just fucking downloading this shit anyways and just pruning like they would. It was assume valid or whatever they're going to do, right? And then the other thing is there is fees for miners to make.
Yeah.
Even see, like if somebody was trying to just sort of like make a very cheap, massive Lightning Taproot script or transaction there that is very low density in terms of like amounts of like fee per byte, right? Like those may lose. So the miner still is, again, making money on this. And then the other thing is the degen JPEG people really value this shit. So like they will, at least in this stage of Bitcoin, they are valid economic actors, right? Like they're like powerful economic actors in this way, right? Their stuff, it will pay. Say, for example, Jay-Z comes tomorrow and say, hey, I want to do 4 blocks in a row where I take the full 4 blocks and I'll pay to make it happen, right? Like, I don't know any miner that will say no for somebody to like pay $100 million per block just to have his full JPEGs on them in a row.
Isn't there like a meta question here? Because I remember years ago worrying about the issue of, let's be really clever and start building off-chain protocols that are really, really useful and powerful, like, I don't know, financial derivatives or something really important. And people need to just like embed certain data into the blockchain in order to like anchor it into Bitcoin. I mean, if you get to a point where other things, it could be JPEGs, it could be derivatives, it could be anything, I don't know, or like a sidechain, like really, really like incredibly useful, and everyone puts huge financial value in them, and they don't that way more than what they're putting into base layer Bitcoin transactions. Is that a problem? Is that a bad thing, or is that a good thing? Is the end of my question.
Okay, so maybe you guys can sanity check me here, right? So I have, like, say we go back to the swimming pool, right? That's where I'm a miner, I'm building a block. Right? There's only so much capacity, right? 4 megabytes of water in there. Base layer transactions are always going to be more economically dense, right? Because they're going to have less useless data
compared to JPEGs, for sure.
Per fee byte, right? So they sink to the bottom. So they make it, right? So all my single UTXO in, single UTXO out kind of transaction, right? With like, even if it's one V byte, right? Like,
but they don't make it in your Jay-Z example, because Jay-Z is going to pay $1 million fee, right? They don't make it there.
Well, in that exact example, yes, I lose.
Well,
right?
that's a broad category of examples where people are placing more financial value on things which are not Bitcoin.
But here's the thing. It's going to be very hard for somebody to have, I mean, Bitcoin is kind of a stupid monetary system if the JPEGs per block are more valuable than the transactions in the long run, right? Maybe we lose 4 blocks in a row because somebody's pulling a stent that is not economically like reasonable, right? But in the long run, it's the same like issue that you have with like any vassal and trying to fill that vassal. The smaller the thing that you put in there is going to have more units than the thing that's bigger, right? And if you add water to this and you create economic density, those things will sink and they're going to make it and they're going to stay in that thing. So my point is the traditional Bitcoin transactions, right, are always going to likely make it on the next block just because they fill in the gaps, while this like massive balloon size JPEGs, right, they may not. And they want them to be like in a single thing as well, right? You can't put half a transaction. So, the bigger that they make them, the less likelihood they have of making into a block as well.
That's true. I mean, I agree with all that. I don't.
For what it's worth, I don't agree. But
okay, well, I'll be quick, right? My concern is with in the long run, right? And I don't think there's any good technical block, so on some level, I just have to accept it. But like, what if in the long run it takes like a year or multiple years for this JPEG hype bubble to go away? And in the meantime, we've been unable to onboard people onto Lightning, and we've been unable to use the network, right? And then what's...
Well, I mean, then likely what we do is we just lose Taproot, right? I mean, we just take it out. I mean,
good luck with that.
No, or you add the limit.
Wait. For listeners, let's be really clear about the difference between SegWit and Taproot on this, right? I mean, yes. Andrew already explained it, but I want to sort of repeat it, but just like change the emphasis. Because to me, yeah, it's true that in the pre-Taproot days, you would have had to split a JPEG across multiple transactions. But that is hardly a problem for an engineer, is it? I mean, that's not very hard. And it would have been slightly more expensive. But I mean,
I don't think the incentives will be there.
I want people to be clear about the numbers here. The difference is like 10, 15%. I think somebody worked out the details. I mean, like you figure it out. It's a very small cost difference between splitting it and having it in one.
I don't think that the cost is definitely adds to the incentives, but that's not the biggest challenge. The biggest challenge really is removing the limit on a script, right?
No, but the fundamental limit is still there in the block. That's the point.
I know, but that's a full JPEG, right? Let me just go back to this, right? Remember the original fight, which was op return size, right? Yeah. Somebody started putting unwanted pictures into it, and then everybody was like, you know what? We should have a limit on this, right? Especially in those days, because there was very few people to go to jail. So nowadays it's no longer an issue. We're not concerned about going to jail if somebody puts a picture that shouldn't be there. But I think the challenge now is that like, what I would say is that like, if what we might get as a pushback from the Bitcoin network in terms of like how to fix this if it truly becomes a unsolvable problem, economically speaking, versus transactions that are for people to pay for stuff.
That's exactly my point, Rodolfo. You will not remove this problem by removing Taproot. SegWit has a
not removing Taproot. Sorry, adding a limit to the script.
Adding a limit.
Exactly. Exactly. Right.
Yeah, that's more feasible at least. But I don't know. But Andrew would have. I want to hear what Andrew thinks about that. What do you think about the possibility of adding a limit?
It would frustrate me. I mean, it's not going to break my heart. So, especially with Taproot, it's kind of convenient because you can kind of like rearrange your script. So in the end, like it's this giant sequence of ORs. So rather than having a script that's maybe like something fairly complicated, right? You could have just like a million individual possibilities, but each one is an individual tap path, and then you only reveal a little bit. So technically, yeah, I could work with it. I'm not going to be heartbroken if I have a network where I can't have arbitrarily large scripts anymore. Now, would this fix it? I mean, you could still split your JPEG across multiple inputs or multiple transactions.
That was always possible, and nobody did it because it's boring. Like, see, you guys are thinking like very practical mathematicians here. See, like they are thinking as like my art is in a block.
Yeah, but I totally agree. But you have to think hard-nosed about these kind of decisions because what we're fundamentally doing is trying to design a system which is resistant to attack, right?
Oh no, I agree. I mean, that's why I'm saying leave it.
Right, you agree. So I get it. Aesthetically, people prefer like one big block of a JPEG, and so therefore you can argue that Taproot is kind of shit because it allows that. But actually, we can't think like that. I don't think at the protocol level. We have to think about the serious attack vectors.
I mean, if it's the way I think about it is these are just like arbitrary valid bytes that people are entitled to make if they pay for it.
Exactly.
Right? If they're sticking like pixels instead of sticking like bytes of a Merkle tree. Like it's none of my business really.
Exactly. Exactly. If I write a crappy, today we ban JPEGs. Tomorrow I write a really crappy new privacy protocol with a really bad script, and someone says that's banned because it's shit. Yeah, because I don't like it. Like you can't have like this kind of normative judgment. I don't think that's the right term for it. You just have to let the economics figure it out. You can't.
You could make the argument that some of the degen DeFi shit that people would stick in Taproot is more damaging to society or morals than the JPEGs are too.
They're not sticking in Taproot. They're not sticking in Taproot.
No, they're not yet.
In Bitcoin.
Yeah, sure, but not yet, right? Like, anyways, but my point is just, I don't think we should be making, we can be angry about it personally, but I don't think we should be making design decisions on Bitcoin based on things that we don't like that are still valid transactions paying fees.
Exactly.
I agree. For what it's worth, I don't think we even, technically, I just don't think you can. Like, the best you can do is make people have to split their stuff up and encode it in something weird, right? But so on some level, that kind of solves the debate because there's not any technical way for me to have my way.
Mm-hmm. Absolutely.
But, that was my like literal my come to a realization point is like there's nothing we can do.
What if somebody starts encoding? I know we had op return in the past. What if somebody starts encoding things in outputs, even though it's going to be more expensive, like 4 times more expensive? Maybe they don't care. What if they start encoding JPEGs in? Well, I'm sure they've done it in the past, like in million UTXOs. Are we just screwed? Are we just totally screwed? I mean, if they do that.
No, I think honestly, that like number go up resolves most of these issues.
Yeah,
because the economic density of those transactions, right? They're going to be so big. Right. Say, for example, because maybe right now we have like 10 million people using Bitcoin, like really using Bitcoin, not like Coinbase. I don't use Bitcoin, right? Like it's like actually have access to your UTXOs. If there is 10 million people, probably exaggerating.
Much less, yeah.
So, imagine when we have like 1 billion people sort of like doing some stuff.
We'll never have 1 billion people owning UTXOs. We'll never have 1 billion people owning coins on.
That's what I'm trying to say, right? Like as we just scale this just a little bit, right? Those transactions, the value of each transaction, economically speaking, has to be so high, but so high in order to warrant its existence in a block, right? That like all these problems go away. We might still see like one-offs, stunts and things over there, but like there is no JPEG economy to clear settlement between payment providers. You know what I mean? Like, if there is, it'd be kind of cool.
So I think you're right. I would invert it though and say like if number go up doesn't solve this, then Bitcoin has failed, right?
Yeah.
Now there's still a question of like right now we're trying to bring people onto Lightning, and right now we're having delays and this is costing people more, and that's kind of unfortunate if like things are squashed in their infancy, right?
Maybe Lightning is just not adversarial enough, because if a state actor was trying to prevent Lightning from happening, it could just sort of like fill blocks.
Right, they could just pay miners to fill blocks with crap. Yeah, and I don't...
Or empty blocks.
Yeah, or empty blocks. Yeah, right, you just pay out of bound, right? Empty blocks would be a little bit nicer if you're going to do that. Yeah, that's always been true. And I guess the defense has always been like number go up. Like it just needs to be expensive enough to mine that it's impractical.
Yeah. Listen, guys, I think this was awesome. Like this was awesome. I might add a preamble to the beginning saying, hey, you might get a little dense, but I don't know. Like I feel like you guys did an absolutely fantastic job at trying to explain concepts and things. It's hard, right? Because like I always like you want to explain farm terms, as I like to say, but like there is no hash function in a farm, right? Like so the meat grinder doesn't really give you a fingerprint. But my point is like I think you guys did like a fantastic job getting close enough to that, given the circumstances of the topic.
Well, can I make a book recommendation? I just suddenly thought if people are listening to this and they've only been joining in with Bitcoin the last few years, maybe read The Block Size Wars by Jonathan Beer if you want to understand a bit more. It's not technical at all. It's about the history of like the debate around SegWit and about the block size increase. And it was a fascinating time. I just think it's a very short book as well. Actually, good read.
Has anyone written couple thousand words on just explaining segregated witness, like to the world kind of thing as opposed to like the mailing list?
I think the We Use Coins website, maybe. I don't know. Do you know Waxon?
Yeah, I think I've looked at that briefly. I think it's got some good technical stuff. But I was thinking about in terms of like an introduction. There was the Blockstream yourselves did a couple of blog posts about SegWit back in the day.
So I have an old website that a bunch of people collaborated.
Oh yeah, you had a website, right? Yeah,
the UASF.org.
Yeah.
We do glance over a few things there, but it's not in depth. I don't know. Maybe you should just like pay somebody to sort of like.
You can watch my talk on YouTube that I gave in London about a year ago about SegWit, about what it actually
Send
is.
us the links. We're gonna add a lot of links to the show notes.
I'll send that link. Yeah.
And maybe now that we had this conversation, got a few things out. Maybe you guys go back and reflect on this and maybe you go like, aha, like maybe I have a much better way of sort of like, maybe, or a different way of like trying to sort of like explain this and sort of go over it. I think it's like super, super important. Like a lot of the grief and a lot of the strife in the Bitcoin sort of ecosystem comes from people just not fully understand what's going on.
It's true.
And it's not simple stuff.
Yeah.
So anyways, very grateful you guys gave me more than 2 hours of your time, and hopefully we'll do this again not too long from now. I also want to maybe have another episode on talking about speedy trial and all that stuff. And any final thoughts, Adam?
No. Apart from that book recommendation, that was my
that's
thought.
good. Andrew,
any final thoughts?
No, this was a lot of fun. Good luck paring it down.
No, we're not paring it down. Like, this is we minorly edit just for like, like delays or things. No, this is, people are going to have 2 hours. I think it was kind of cool. I was kind of paying attention a little bit, but it feels like there was an arch that we built that sort of like tied everything sort of like back in, like in a nice little, in a circle there of like where things started, where things ended. So yes, thank you so much, guys.
Yeah, thank you.
Thanks for listening. For more resources, check the show notes. We put a lot of effort into them. And remember, we don't have a crystal ball, so let us know about your project. Visit bitcoin.review to find out how to get in touch.